This is a little test. Those you should now be seeing a presentation from
Hi, Leonard, it's Ian. I can see the presentation on Zoom, but not. Oh no, it's just appeared on YouTube.
Okay, great. Thank you very much.
I don't know if there's a lag between the two there.
We couldn't test YouTube until this very minute, so apparently
Okay.
that's good to know. Thank you.
But yeah, it's appeared there now.
Let me. Okay, so I'm just scrolling up and down on some of the slides. Okay, thank you very much. Okay, I'll stop sharing this because Peter will have a proper introduction in a minute. Okay, Peter, welcome. And I just made you a co-host, Peter.
Thank you.
And I've already started the YouTube streaming, and Ian just confirmed that when I showed a slide of mine, that was showing for him on both the Zoom and the YouTube channel. And maybe we should try the same for you. And you should now be allowed to share your screen, in fact.
Conveniently, it shows me no sign of whether I'm successfully sharing anything.
Yes, I can see it on Zoom, and let me see on.
It seems to have a much better latency than Google Hangouts.
On YouTube, I can just see the list of participants currently, but not Peter's presentation yet.
So Peter's slide appeared for me 25 seconds after he put it on. I saw it on Zoom. So it's kind of live. That'll do.
No, I see it on YouTube. With no person in person or anything, it's just the slides. And very slow to update.
Wow, I just got my presentation on YouTube now, about 2 minutes after the. You should now be seeing a presentation.
Maybe Joseph and Ji-Young should check that they can also share something while we have a few moments.
Actually, I'm seeing this huge latency between Zoom and YouTube as well. So I don't know if it would change if I share something. Do you want me to test?
Probably yes. I'm totally clear where in this interface I can stop sharing something.
Usually at the top of the screen, for me, there's a few options and then a red.
It was like tucked away on a different monitor. Yeah. My screen sharing is now paused, so Joseph?
I can still see your screen, so yes, there is even a lag there. I think I can kill you if you'd like me to, your screen sharing. But
Well, I paused it, which I had hoped would pause it, but now I've stopped it.
I think pause means that we can still see it, but it doesn't change, whereas stop means we see you now rather than the screen.
Yeah, that's not terribly useful of it, is it? Anyway, Joseph, try yours.
Yeah. Then your guy's asking on the chat whether he should maybe improve the latency at the price of lowering the video quality.
You could try it and back off if the slides are not readable.
Yeah.
I thought we were going to disable Zoom group chat in favor of getting everyone to use Slack.
Yeah, maybe for these management issues, it's not too bad to use the chat. But
Yeah.
yes, once we start, we will. So, Ji-Young, would you like to try and share your screen as well?
Okay, I'll try right now.
Yeah, what showed up for me on the Zoom channel at least.
So I'm flickering my slides, and did anyone see how long it takes for YouTube?
Just switch to the distributed systems challenges slide with
Yes.
at the top. Yeah, just as you were starting to speak. And now you're at the one with the full pictures. Yes.
Yes. I guess that's almost.
Yeah. And Peter, I haven't started the recording yet, but if I interpreted our experiment yesterday correctly, then each time we press and stop the recording, sort of a new pair of files is generated. So we can do that either on a session-by-session basis or on a talk-by-talk basis.
Probably easiest to do it talk by talk, so we don't need to mangle them afterwards.
Yeah.
Did you discover the you might be being recorded notice thing in Zoom?
No. So maybe we should announce that at the beginning of the workshop. But since people know that it's streamed on YouTube anyway, and people have already asked on the PLDI channel whether the conference will be available later on, I don't think people will be very surprised.
Yeah, indeed.
But since we're both hosts, we should probably coordinate who of us operates the recording. Otherwise, you will switch it on and I'll switch it off.
I'm not. The emails go to you.
Yes.
I think it would be better if you did it. Therefore.
Okay. Let's see where we. Yeah. Okay. First time too. Oh, did you yesterday each time stop recording or just pause it?
I stopped and started a few times.
Okay, so then stopping will actually create new files, and we just started it now, so I'll stop it and then start it again when we actually stop.
Okay, are we ready to go?
About time, right?
Well, if you start recording.
Okay, yes, I just started, right? Connecting server. Yep, it should now be running.
Okay, then welcome everyone to this REMS DeepSpec workshop. Lennis and I will do just a quick intro. So we have here some highlights of these two projects and one invited and one submitted talk, 6 40-minute slots each day. I think in the end all of these will be live so that hopefully we can have some interaction during and after the talks. And if you have questions, please ask them on the Slack channel, and whoever is chairing will forward them to the speaker. We might interrupt the speakers partway during the talk if that seems to be a good idea, or they can choose to pause for questions, whichever. Thanks, obviously, to the PLDI organisers and volunteers and everybody, to our PC, to all our speakers, and to you for coming along to this umpteen and once video meeting of this season. There's a schedule, you know what that is. So I'll talk for just a few minutes about REMS and then Lennis about DeepSpec. So for those of you that don't know, so REMS has been a UK EPSRC program grant. This is a fairly large grant that in the end ran for 7 years. What I'm going to talk about and what the REMS part of this program is about is not all funded by REMS, but I think it's fair to say REMS was the spur for all of this. And then in Cambridge and Imperial and in Edinburgh, which are the 3 sites, we also now have various other funding which has supported some of what's going to be talked about. Lots of people involved. So those 3 universities, that's not too surprising, but more unusual is that this is really a mix of semantics and PL folk with some hardcore systems people, so operating systems and computer architecture and security and networks. So here are the PIs, John Crowcroft, Neil, Simon Moore, Robert Watson, Philippa Gardner, Mike Gordon, Neil Krishnaswamy, Andy Pitts, myself, and Ian Stark. And then lots of researchers, postdocs and students and interns involved over these years. So rigorous engineering for mainstream systems, what does that mean? Well, the basic question we ask ourselves is, how can we use rigorous semantics to understand and improve the systems that we all use and depend on all the time, and the engineering processes that people use to build them? So that is the processor architectures, the ubiquitous programming languages, linking, various operating systems abstractions like POSIX file systems, network and security protocols, all of this kind of stuff that is pervasive in our infrastructure. And the core idea of REMS is to take these existing artifacts and the reasons that they are what they are and the cultures that build them seriously, and see how we can improve things and apply semantics for good from there, rather than starting out by focusing on maybe a better and more ideal world that we would prefer, but is not straightforwardly reachable. So that means that we're choosing our target scopes and our abstractions very carefully to make the work possible, but we are not idealizing or oversimplifying. So where does that take us to? If you look at that pile of infrastructure, it's enormous and also rapidly changing. But if you look at the interfaces between them, the architecture specifications, the PL definitions, and so on, these are still pretty large and intimidating by academic standards, although quite small by code standards. But they are manageable and relatively stable, so they're good targets for us. So then we're also taking mainstream system development processes seriously. All of this is built with test and debug development, testing executable code against basically manually curated tests. And they have to be manually curated because what we have are only prose specifications for all these things. So one of the focuses of REMS is to establish specs which are executable as test oracles, i.e. that are sufficiently computational to let one decide whether some observed behavior is allowed or not. And then that lets you do all kinds of things for testing and for validation, both of implementations and of specs. We are certainly not building models for their own sake. Instead, we're doing this to elucidate what these abstractions are, in some cases what they should be, and in many cases, it's turned out to be very unclear what they are, even to the industrial designers that make them. And then, based on them, to enable practitioners to routinely use somewhat more precise engineering methods using these specs. And this is stuff that fits in with the existing industry practice, right? It is adoptable. So we would like in the long term to support formal verification and analysis based on these models, and people are doing some of that now, but REMS is not principally aimed at full stack verification, right? We're aimed in the first instance at the shorter term and more attainable goals, but for these real systems where verification is still basically out of reach. There's also a research culture goal here. So we want to do this for deployed systems, but also for large-scale systems research projects. And these mean that we have to establish collaborations between the semantics folk and both those systems researchers, and in practice this has been mostly the Cherry team, and the industrial systems builders that we speak to. We're academics, we write lots of papers have come out, but we're not really talking here about those. What I'd like to focus on, and in the REMS part of the program, we have 6 of these, are some of the substantial sub-projects looking at individual abstractions and sometimes linking them together, which is very instructive, for C and WebAssembly and multiprocessor concurrency, multiprocessor instruction set architectures, the Cherry capability system, and the Gillian symbolic evaluation tooling from Imperial. So for each of these, there's some major industrial or systems research collaboration with the relevant groups in each case, and we'll see some of that in the talks. Then, last thing I'd like to say is that this is producing a lot of models and tools, and we really want these to be widely usable. So we're sinking a lot of engineering effort into making them be as solid as we reasonably can. Lots of these are packaged up. Lots of links on that webpage. Please use them, talk to us about using them, give us feedback, do new remarkable things that would not be possible without these as a starting point. So that's my REMS introduction. Lennart, over to you.
Thank you very much, Peter. So yes, I'll give a similarly short summary of aspects of the DeepSpec project before we will then start with the actual workshop. The Science of Deep Specification has been an NSF expedition in computing funded for the last 5 years. And it involves 4 universities on the East Coast of the US. And it is motivated by the world that we lived in 4 years ago and to a large extent still live in, which is often characterized by computerized systems that show very surprising behavior, including exhibiting insecurities and allowing people to invade on each other's privacy or do even more harmful things such as snooping on communications, hacking into each other's cars, and attacking industrial control systems. Now, of course, the programming language and formal methods community has, for the last 30 or 40 years, been trying to help defend and protect against such attacks. And there's a big design space of for methods and techniques where one could attack could aim to solve these issues. So, and these range from more informal specs that are still describing behavior at a very detailed level, but are in informal English or semi-formal descriptions, to more formal traditional specification languages, such as maybe VDM or Event B. They have been developed over 40 years and were already several years ago equipped with very usable tools, but sometimes, but one of the characteristics they also have is that they are not fully connected, not always fully connected to the actual code that is verified. They often operate mostly at the model level. Then there are, of course, static analysis and type systems that are connected to actual code, but are not as expressive and thus only help to, for example, ensure safety properties rather than full functional correctness. There are other analysis techniques such as model checking. There's lightweight verification, so very widely used verification tools such as Key or Daphne in the design by contract method, that again is at a slightly different point in this large design space. But what our project was really inspired by were projects that emerged over the last 10-15 years, such as the SEL4 verified operating system kernel and the CompCert verified C compiler, and also work on verified hardware architectures in Austin, where one uses the expressive power of interactive proof assistance to have a very expressive specification formalism and at the same time link to actual artifacts that are executable or generated then. So one of the ingredients, in addition to the traditional programming language abstractions and reasoning structuring principles, is really that all these systems that emerged over the last 10 years really took a modular approach that went beyond the traditional structuring principles of the systems they were looking into. So for example, CompCert gained a lot of its success by its partitioning of the compiler infrastructure into many intermediate languages and translation phases, which then allowed the developers to give formal operational semantics in a proof assistant to each language and prove the translations formally correct. Similarly, in the structure of operating systems, and here I'm showing a picture from the Sodikos team at Yale, they managed to structure the operating system, which was in this case mostly designed from scratch, in a novel way that identified lots of individual components that could be separately specified in a coherent framework, which they called the compositional abstraction layers, and could then compose these individual components by proof, again in a proof assistant. And similarly in our project in Princeton, where we focus on verification of C programs, we try to be, again, exploit these principles of modularity both horizontally and vertically. So on the vertical axis, we want to separate the actual code verification of the C program from the reasoning about what the program actually does. And for the latter, it is very useful to exploit the functional language inside the proof assistant, or maybe a relational propositional specification style, but separate that from the particularities and details of the C language. And on the horizontal axis, we want to match the modularity in which code is actually designed as much as possible when structuring our code specifications and verifications. Now, you already see that all these projects here I mentioned use the COC proof assistant. And yes, the use of a uniform proof assistant is a starting point to go a step further. And that is what the DeepSpec expedition has been about. We started from the observation that these individual components have very nice specifications although these are still continuously be improved, but they are isolated, and the specifications of the operating system API, for example, designed in one project is not necessarily matching up with the assumptions that are made by a client program. And similarly for the assembly language with respect to the processor architecture and other interfaces. So our vision has been to move from these individual components, individually specified and verified, to a more integrated view where it is possible to link them up. So the main tasks has been to connect, for example, the verification structure of VST to a verified compiler of CompCert, to work out what the contracts are between the source program and the operating system, here shown in green, for example, and similarly between all the other components. And do this for application programs that actually interact with the outside world. And as I mentioned before, that will not come as a surprise to many of you, the use of a single proof assistant is a good starting point for that. But of course, it's not the entire answer, because even in a single proof assistant, you can model very different models and model them in a very different style. So the use of a proof assistant gives you at least the platform to begin connecting such components, but there's still a lot of work done. So my last slide here, I show just a summary of the many interconnected projects that play a role in the DeepSpec project, and you will hear about many of those in the next 2 days. I'd like to, as a cross-cutting issue, briefly point out one aspect that, one technical aspect that we have developed. So as it has really emerged over the last 4 years, a widely used pattern of reasoning about effectful programs inside COG, which is formalized as interaction trees, and really has been good to connecting several of the components in the different sub-projects. So it's executable. We have a property-based testing tool, a QuickCheck, which can be connected to interaction trees. Interaction trees are embedded in the VST, so you can actually verify interacting programs in VST by relating them to the interaction trees. That enabled us to specify I/O in an application that has driven a lot of these integration work and a little web server domain. But it originally, at least in this main formalization, originated from the development project, which Yannick Tsakowski will talk about tomorrow. In addition to these scientific projects, we've also had lots of activities on helping the community, both for curriculum development and exercising this in courses in our institutions and also in summer schools. We ran 2 summer schools in 2017 and 18, had hoped to run one this year. That has, of course, been canceled and postponed to next year. So those of you who are interested in participating may probably have a chance to apply again next year. And with that, I'll just finish this little overview and look forward to lots of interactions and the talks of the other presenters today. Okay. Do we have any questions, or otherwise I propose we immediately start with the first session. In fact, let me just pause the recording quickly. And then so our first speaker is Joseph Tassarotti. And without from Boston College, where he's been an assistant professor for a couple of years now, and he's talking about verifying crash-safe concurrent systems with Perennial. Thank you very much, Joseph.
Okay, can you hear me?
Yep.
All right, thank you very much for the introduction. Yeah, so today I want to talk about some work that I've been doing over the past 2 years with collaborators at MIT, in which we've been developing a framework to prove crash safety of concurrent systems. So let me start by motivating this subject and elaborating a little bit what I mean by crash safety in this context. So if you think about storage systems that are used to manage data, things like file systems, databases, or large key value stores, oftentimes those systems need to be implemented in a concurrent fashion for performance reasons. And in addition, they're expected to be resilient when a program crashes or is interrupted, in the sense that we don't want them to lose data. And just to clarify, because I think there's a little bit of terminological differences between the systems community from which this work sort of originates and the PL community, when I talk about a system crash, what I mean is an externally generated event, something like a power being lost or a process being killed abruptly, that causes a program to stop suddenly. So they're external in the sense that there's nothing a program can do to prevent them, so to speak, and they can occur immediately at any moment. Okay, and so when we think about something like your file system, if your computer were to lose power suddenly, you should really like that when you restart your computer, your whole file system isn't corrupted. Okay, so resiliency in the presence of these kind of interruptions is what I mean by crash safety. And now, an important way in which programs achieve this kind of crash safety is that when the system restarts, we will generally need to run a special procedure that we're going to call a recovery procedure that restores various system invariants and makes sure it's safe to run normal programs again. All right. What's tricky here is that while we're running this recovery procedure, in principle, we could once again have another crash. You could lose power again or something like that. And if that happens, then we're going to need to once again restart and rerun the recovery procedure and so on. And we want the system to not lose data, even if this takes multiple rounds of interruption and running of recovery. When we finally manage to complete recovery, we'd like the system to be in a good state. So reasoning about concurrency and crashes is quite tricky. I think we all know that concurrency verification by itself, even setting aside crashes, is not so easy, and there's been an enormous amount of work tackling that and developing frameworks for doing such verification. But when you mix in crashes, things actually get quite a bit more complicated because of interactions between concurrency reasoning and crashes. So in particular, if you think about common concurrency control techniques like using locks to protect access to a data structure, well, normally we like to think, well, when we have this lock, no other thread can observe the intermediary states of what we're doing as we manipulate the data structure, right? But holding a lock does not protect you from interruption by a sudden power failure. And so even if you were holding a lock, when the system restarts, the recovery procedure I just described is going to be able to observe intermediary states that would otherwise have been protected by the use of the lock. Another issue is that when we think about what this recovery procedure needs to do, it often has to either roll back or finish up operations of threads that were crashed. So when we make an argument sort of both intuitively and formally trying to justify its behavior, we need to sort of refer back to what the heck was going on in the middle of execution when we were previously crashed and make some correspondence between crash threads and what recovery is trying to do. So our contribution is a framework that we call Perennial, which allows one to prove this kind of crash safety property for concurrent systems. So the framework is mechanized in Coq, and it's built as an extension to the Iris concurrent separation logic framework, which means that sort of for free, we inherit a lot of features of Iris for reasoning about tricky concurrency patterns. And in order to be able to verify real systems code using this framework, we wrote a tool called Goose, which translates a reasonably rich fragment of the Go programming language into a format that we can verify in Coq. Okay, and we've used this tool to verify a couple of examples. So a bunch of what I would say are sort of toy or simplified programs that illustrate common techniques or programming patterns that are used to achieve crash safety. Things like logging, shadow copies, and replication across multiple systems. So if you're not familiar with some of those techniques, that's okay. The point is just that if you read about how file systems actually achieve this kind of resiliency, you'll see these techniques mentioned. So we wanted to demonstrate the generality of the framework. And in addition, we verified a Go implementation of a kind of mail delivery agent. So something that writes out email messages to users, directories, and we prove that even in the presence of crashes, users won't see malformed messages, and we won't lose messages that have been durably written out to disk. So I should say that this talk, I'm going to sort of describe what I would call Perennial 1.0, which is described on our SOSP 2019 paper. But of course, since then, we've been doing a bunch of additional work. And in particular, we're now using Perennial to prove the correctness of a network file system server that we implemented in Go. And I think as anyone sort of in this community knows, when you actually scale up and do even larger systems verification, you come up with a bunch of new ideas and so on. But as those are sort of still in progress, I'm just going to focus on what we had described in the initial paper. Okay, so let me start by describing sort of the core technique that is used to reason about the possible interruptions by crashes. And actually, in order to describe how things go in the concurrent setting, I first want to describe some earlier work on establishing crash safety for sequential systems. So several of my co-authors with their collaborators a few years back proved crash safety for a sequential file system they wrote called FSCQ. And the core proof technique that they used was a program logic they developed called crash Hoare logic. So in crash Hoare logic, instead of proving a Hoare triple, one proves a Hoare quadruple, like the one I showed below. So it has both the standard precondition P and postcondition Q, which have their usual meaning. But in addition, we have this extra assertion R that's called a crash condition. The idea here is that if you establish this quadruple, in addition to the standard meaning of a Hoare triple, you know that at each intermediary step, the assertion R holds. Okay. Now, if we want to generalize this to the concurrent setting, an observation that was made in an earlier logic called fault-tolerant concurrent separation logic from Gardner's group at Imperial, and an idea that we also use in Perennial, is that we actually don't need this quadruple mechanism. We can use standard triples and actually reuse existing mechanisms in concurrent separation logic for doing invariant-based reasoning. Because if we think about what this crash condition is from the way I've described it, it's something that has to hold, before and after each step of execution, which is the definition of an invariant. So since concurrent separation logic already has invariants for reasoning about the interactions between different threads, we can just reuse that. All right, so let me just actually describe for people who are not so up to date on all the developments in concurrent separation logics, how invariant-based reasoning in these logics works. So here I'm giving kind of a schematic diagram. We think we have a collection of threads. Here I'm just showing two threads, 0 and 1. And we're in some initial state sigma 1. And what we do is we think of each thread as owning or having access to or controlling some section of program state or some collection of resources. And those resources are described by assertions in the program logic. So here, thread 0 has access to P and thread 1 has access to Q. And I've sort of drawn a separating conjunction in the middle here to correspond to the fact that we think of these as disjoint pieces of program state. Right? And in addition to what the threads own, there is some additional piece of state that is devoted to an invariant, which is described by an assertion R. And now what you usually find in these various concurrent separation logics is that there will be a rule that when thread 1 is taking a step, before the step begins, we can pretend as if that thread had access to the resources in the invariant. So we imagine almost like R was added to the precondition of that thread. And then when the thread takes an atomic step, it's going to perhaps update the state and bring us to some state sigma 2. And in the process, it may modify the resources it has access to. So now perhaps instead of Q, we have some Q prime. And then what we have to do is show, though, that the invariant R still holds and corresponds to some disjoint piece of program state represented by using a separating conjunction. And then we put back that R back into sort of the invariant bucket, and the thread goes on just holding Q prime. So this way now, if some other thread, say thread 0 here, takes a step, it too can assume that R holds in its precondition and use the same mechanism. So this is a technique for kind of encoding some sort of rely guarantee style reasoning as you build up more generality in these logics. So if we want to reuse this to think about crashes and the way the crash condition and the crash for logic work, well, if we imagine, right, so say we're in that same scenario, and let's say thread 0 takes some step, thread 1 takes some step, and of course they're using that rule I illustrated on a previous slide. So at each moment, we still have that this invariant R is preserved. Well, now if the system were to crash abruptly, right, denoted by this red squiggly line, then in the same way that we know that R holds at the beginning of each program step, we also going to know that R held at the moment of crash. Okay, so this allows us to get away from having to have the Hoare quadruple, and we can just reuse this existing invariant mechanism. So that's a sort of the maybe key insight for how you can reuse some mechanisms from concurrent separation logic to do crash safety reasoning. But there's actually quite a bit more that has to go into tying all these things together and actually completing a crash safety proof. So I want to talk now about some of those ideas that we use in Perennial in order to make this all hang together. So in order to describe these ideas, I'm going to need a running example. And what I'm going to do is describe a disk replication system. So this is a library that presents an interface of a single reliable disk to clients of the library. And it does so by implementing this on top of two potentially unreliable disks. And the way it works is that when, say, a write or read request comes into library, the implementation of those routines in the library actually mirrors those operations across the disks. And to make things interesting, we're going to allow for the possibility, in addition to crashes, we're going to allow for the possibility that one of the disks could fail. And when that happens, the system is going to service subsequent reads from the mirror copy. All right, and of course, if both disks were to fail, there's not really much you can say anymore. So we're just going to consider the scenario where at most one disk could fail. So here's a sort of very idealized snippet of Go code that you could use to implement the write procedure here. So the way we're going to make this thread safe is that we're going to have a lock for every address. So the write procedure takes an argument of the address A you want to write to, and a slice or an array of bytes that you want to write out to that block on the disk. So to start, what you do is you acquire the lock corresponding to address A, and then you write the value to both disks at that address, and then you release the lock. All right, in the read procedure, I won't show the code, but it's very similar. You start by acquiring the lock, trying to read from disk 1. If disk 1 is non-responsive, then you read from disk 2 and return the value. Okay, so informally, we can think the reason why this makes sense and is thread safe is that the lock here ensures an invariant that when the lock is not being held, we know that the two disks are in sync at that address. So they have the same contents there. But if we think about what would happen if we were to crash after line 3, but before line 4. So we've written out the value to disk 1, but we have not yet done the write to disk 2. If we crash then the disks are going to potentially be out of sync at that address. And since this is current, it could actually be out of sync at multiple addresses. So when we restart, we need to run a recovery procedure. Again, here is an extremely idealized Go snippet for implementing recovery for this system. The idea is it's just going to iterate through every single address on the disk and copy over what's currently on disk 1 to disk 2. So just imagine that disk reads return a Boolean flag OK, which indicates whether you actually were able to read a value out. So if the read succeeds, then we copy that over. All right, and of course, in a real implementation, you would be much more efficient. You wouldn't want to copy every single disk address over, but I think this illustrates the core point. So even if this procedure is interrupted by subsequent crashes, we can see intuitively that when it finishes, right, the two disks are going to be in sync. They're going to have the same contents at every address. All right, so how would we go about proving this property? Well, first, actually, let's just set aside the crash issue and think about how the concurrency proof would go in standard concurrent separation logic. So the way that I would sort of do this proof, and I think many people would, is, well, okay, in addition to the points to facts that we would have for reasoning about the contents of memory cells, we're going to naturally need points to facts that describe the disk contents. So I'm going to write that as a D subscripted by a disk number, either 1 or 2, and the address, and then an array of bytes. So that will say that at address A on disk I, we currently have the block of V. All right, so you would have these primitive resources for manipulating both disk state and memory state. And then what we would do is write down lock invariants that capture the intuitive explanation I was giving for what the lock is trying to do. So the lock invariant for address A would say, well, there should exist some value V such that both disk 1 and disk 2 at address A point to that value V. So that captures that they have the same contents at that address. And of course, in a real proof of complete correctness, you probably would need to track some additional details, but this aspect of the lock invariant is this property of synchronization. Okay, and then you would use standard rules in concurrent separation logic for working with locks. So in particular, these rules allow you to what we call acquire ownership or transfer ownership of the resources described by the lock invariant. So in particular, if you lock the address, then in the post condition, you get the lock invariant at that address. So you would have P of A, you would own the two disk points to facts and be able to write from or read from the disk at those addresses. And then after you're done completing your operation, you would call unlock. And the precondition for unlock requires you to reestablish or show that the lock invariant holds. And then in the post condition, you lose that P of A. So you no longer have possession of the resources protected by the lock, which is necessary so that the next thread that acquires a lock can get P of A. All right, so that's maybe using these basic ingredients, you could carry out a proof for just the concurrency aspects of this system. All right, so now what goes wrong when we try to adapt this proof technique to the crash setting? So first of all, we have to think and re-examine the question of what these points to facts should even mean in the presence of crashes. Right? So in standard concurrent separation logic, when a thread has some points to fact in its precondition, we typically think of it as if that thread owns that region of memory. No other thread can manipulate that address, and that's what entitles us to be able to use the standard read and write rules. But if we think about what happens when the program crashes, by its very nature, crashing is going to potentially transform these resources. So you can't think of it as sort of exclusive ownership that prevents others from modifying things, because in fact, a crash can modify the resource. And the way resources are treated by a crash varies. So our disk points to fact, we're going to assume this is a stable, reliable disk. If something is durably written, then it's still there, even if we crash. It may be the case that the disk has failed so that we can no longer, our reads are no longer succeed, but we're just going to imagine, though, that the things are still there on disk. Okay, so that points to fact still guarantees something after a crash, but the memory points to facts, M points to V, that becomes irrelevant after a crash because memory is supposed to be wiped out by a crash. We're going to assume this is some sort of volatile RAM. And so just because you knew M pointed to V before the crash, after the crash, that does not license you to read from memory at that address, right? That may not even be allocated anymore. All right, so we need to figure out how to deal with this changing nature of resources as a result of crashes. So what we do in Perennial is, for memory, we're going to index it by what we call a version number, which I'll write using metavariable gamma here. So now it becomes M points to V at version number gamma. And what you could think is these version numbers sort of track lifetimes of resources. So when we crash, this version number is incremented, and when we go to use proof rules, we can only use M points to V at gamma if the current generation or version number indexed by our Hoare triple is for that version number gamma. All right, so this means that even if you had M points to V at some gamma, after a crash, that fact is not useful anymore, which sort of captures the idea that all the memory has been wiped and you need to reallocate any memory addresses you want to use. All right, so that's first sort of trick. The second issue is if we think about the lock-based proof I was describing, well, after the crash, recovery needs ownership. It needs these points to facts for the disks at every single address, because it's going to read from all the disk addresses and copy over, potentially doing writes to disk 2. So we put those disk points to facts in each lock invariant in the proof sketch I was describing. The problem with that is that the standard rule for locks in concurrent separation logic says nothing about that lock invariant while a thread has the lock. So when a thread uses this lock triple and gets P of A in its postcondition, after that it's at liberty to do whatever it wants. Okay, which means that unlike the standard invariant technique I was showing schematically at the beginning that you can use in concurrent separation logic, once your proof uses locks, that doesn't behave in the same way. You don't know that P of A is holding at intermediary points. In fact, we know it is not holding at intermediary points because the writes will violate the synchronization until they're finished. So we need some mechanism to deal with that. So the idea that we had in Perennial is a technique that we call leases. So whenever you have some durable resource like that disk points to fact, what we do is we actually break it into two distinct assertions. So one, we continue to write as a kind of points to fact, which is annotated again with the version number gamma. And then the second resource is called a lease. It's also indexed by the version number gamma and records the current value of the address. And what we think is that the the points to fact on the left represents, so to speak, durable, long-lasting ownership of this disk address, whereas the lease just represents an ephemeral right to access the disk in the current version number. So now when you want to write to a disk, you have to use both the points to fact and the lease in your precondition. And then, for example, the write rule afterwards will give you back the updated points to fact and lease. Now, the idea of splitting these things up into two resources is that when we have a crash, the durable points to fact is allowed to generate a new lease. So if we have the points to fact at gamma, we're allowed to transform that into a points to fact at the next generation, the next version number, gamma +1, and a lease for that next version. Okay, so now that's the sense in which this is a durable, long-lasting ownership, because you can always use it to regenerate leases. So even if a lease is lost, we can still make use of this disk points to in the next version number. Okay, so now with that mechanism in place, we can replace the lock invariant that we had before. Instead of storing the points to facts, the lock invariant is going to just store the leases for the address on those two disks. So this still captures the fact that the values are synchronized. All right, but now the nice thing here is we're saying that holding the lock only grants you ownership of this ephemeral resource for the current course of execution. And then what we do is we put the durable points to fact in a standard concurrent separation logic invariant, so that we know that at crash time, that is still going to hold, even if a thread held the lock. All right, so that's sort of how we adjust the resource interpretation that you find in concurrent separation logic. I actually now, and you might think this is a little bit of backwards, I actually now just want to clarify the correctness property that we established the framework with. And that's a notion of what we call crash refinement. So Perennial, we use to prove a relational property. So we have some specification that describes the allowable behaviors of the program. And then what we want to show is that the behaviors of our implementation are a subset of the behaviors of the specification. Now, the usual proof technique, or a common proof technique you would see for proving these kinds of refinements is to use a simulation argument. So in the non-crashing case, the way these kind of simulation arguments might go, say for the write procedure here, is we think of the states of the specification system. So here, I'm going to use S. So S0 is the state before we would complete the write, and S1 is the state afterwards. And then we have the states of the implementation or the concrete code, which I'll use a meta variable C for. And for these kind of simulation proofs, what we do is we come up with an abstraction relation that's going to relate states of the specification to the concrete implementation states. All right. And then what we show is for each operation that the specification has, if we start from initially related states, then when we complete the operation, we'll end up in related states. So in particular, as we do this proof in the concrete code that implements the write routine, we start with the lock. That brings us to some intermediary state. Then we do the first write. And then when we've completed the second write, that's the moment at which we think of the specification state as transitioning and completing its operation. This is, so to speak, the linearization point of this concurrent piece of code. And it's at that moment that we've reestablished this synchronization property, and the abstraction relation holds for this new S1 state. So we still use this kind of simulation argument in Perennial for normal executions, but when there's a crash, we need to change this diagram a little bit. So let's think about what happens in the interesting case in which we have a crash after we've done the write to the first disk, but have not yet written to the second disk. Okay, then after we restart and do recovery, recovery is eventually going to reach that address and copy over the value from disk 1 to disk 2. So at that point, we can think of recovery as having completed the write that the specification, or that the crash thread was trying to do. All right, and so we call this idea recovery helping, in analogy to a technique that you see in concurrent data structure implementation called helping, where a thread will complete operations for other threads in order to batch things and achieve efficiency. But here, it's not a thread completing a pending concurrent operation, but rather recovery completing an operation that was going on before the crash. Okay, so and it's at that moment now that we can think of the specification program as completing that write transition, and then we think of the crash actually taking place afterwards for the specification level program. So how do we do these kind of refinement proofs in Perennial? Well, oh yeah, and as I say, so this is really thinking of completing this interrupted write. So the way that we do these refinement proofs is that we can actually reuse an earlier technique that Aaron Turon, Derek Dreyer, and Lars Birkedal developed for doing refinements in concurrent separation logic. And their idea was we could represent the specification program as a special kind of ghost resource. And we could also represent the state of that specification program as additional ghost resources. So in particular, we extend the logic with an assertion. This J points to, so J here is some thread at the specification level, and it's going to point to some expression E running in some evaluation context K. And then the idea is that the logic will now have rules for simulating steps of the specification program by transforming this specification resource. All right, and now to prove a refinement, it's very clever. Actually, what you do is just prove a triple about the program E, where in the precondition, you have that some thread points to a specification program E spec, and you know that there's a concurrent separation logic invariant R, which represents the abstraction relation between the specification and the concrete program. And then in the post condition, you have to show that the value V returned by the expression E, it matches or is otherwise related to a possible value V that you could get from the specification program. And the rules of the logic enforce that because you can only modify this J points to fact by simulating steps described by the semantics of the specification program, by the very fact that you prove such a triple, we can construct the kind of simulation diagram that I illustrated for standard simulation proofs. Okay, so now how do we adapt this to get those crash simulation proofs? So we have to add a new way to represent that a specification program is in the middle of crashing or has completed a crash transition. And then in addition to proving triples, these refinement triples about every specification level operation, we also require that you prove a triple about the recovery procedure you're trying to use. Where in the precondition, you track that you sort of have the right to execute a crash for the specification. And instead of the standard abstraction relation R, you have a weaker, potentially different abstraction relation Q. Okay, and this sort of just captures the fact that after the crash, perhaps the standard abstraction relation does not hold. And in fact, it's recovery's obligation to show in the post condition that it has reestablished the abstraction relation R and completed simulating a crash step of the specification code. All right, so now if you prove both triples about all of the specification level operations and this recovery procedure, now when you do these proofs, you're going to have this implicit version number gamma that I've been talking about. And what you'll have to show is that from the abstraction relation R at some version number gamma, you can prove the abstraction relation for the recovery procedure Q at that subsequent version number. And similarly, to handle the possibility of crashes during the course of recovery, you have to show that a crash when we had Q at some generation gamma entails Q at that subsequent version. And just by proving this collection of triples and these sort of relations between these invariants, you can establish a crash refinement diagram like I was illustrating before. Okay, so I think, well, we started a little bit late, but I think that's probably, I'll just quickly wrap up. The main idea is to handle the sort of recovery helping idea where a recovery procedure needs to complete an operation of some pending thread. Well, Turan et al. Showed that you could do concurrency helping by transferring this J points to fact between threads using invariants. And we can use that same idea for recovery helping. What we do is, if there was some pending operation that needs to be completed, we transfer that J points to fact to recovery through these invariants R and Q that we set up. So for the replicated disk example, the abstraction relation R we're going to have says that for every address A, the two disks will point to some value at that address. And in addition, if those values are not the same, then it must have been the case that there was some thread trying to do a write for the value that's at disk 1 and was interrupted by a crash. So now, if this is our abstraction relation, when we reason about recovery and we get to this address, we'll be able to argue that what recovery is doing is actually just wrapping up that write that was interrupted. Okay, thank you very much for your attention. So as I say, Perennial is a framework for doing these kind of concurrent crash safety proofs. I would say there's 3 key ideas: the fact that we can reuse concurrent separation logic invariants to think about crash conditions. We had to introduce the notion of leases and versioning to handle the ways that crashes modify resources. And we have this idea of recovery helping for reasoning about active recovery procedures that are supposed to complete pending operations. Thank you.
Thank you very much, Joseph. Very nice talk. I see one question on Slack. Derek Dreyer is asking, in Iris lingo, is the lease predicate just a frag and the durable points to fact is an auth? I'm trying to get intuition, and maybe you can explain what a frag and an auth is for those.
Yes, so this is a pattern in Iris for this. It's very common that you have a scenario where you need to store, where you need to do this similar pattern of splitting up ownership of some resource into what we call the authoritative copy and a temporary, less fragmentary copy. So to answer Derek's question, yes, that is the underlying implementation under the hood. There's one little additional wrinkle, which is that we have to handle this idea of generating a new matching lease in the subsequent crash at that future version number. But the underlying ghost algebra or resource algebra, yes, is this exclusive and fragmentary pattern. Yeah.
Okay, thank you very much. Any other questions? You have 20 seconds or so to type something in. Okay, in that case, let's thank Joseph again for his talk. And if you can hand over the share screen functionality to the next speaker.
I see another question has just appeared.
Okay, then maybe we can still answer that. Paulo Giarusso is asking, would this technology help verifying things like, if I remember correctly, soft updates from BSD file systems, which were infamously hard to get right by hand?
I'm not familiar with the details of that, but I hope so. If indeed you have to handle this idea that there's an interruption by a crash, then presumably some of these ideas could be used for doing that kind of verification.
Okay, thank you very much. So wait, let me just restart the recording, sorry.
I guess so. I guess we should stick to our advertised times as much as we can.
That's correct.
Which means we have 5 minutes off.
Yeah. So our next speaker is Ji-Young Shin, who is a research associate at Yale University and is going...
Leonard?
Yeah.
So we advertised the next one at 14:05, so maybe we should wait for those 5 minutes.
Oh, right. Yes. I'm sorry.
So we can chat in the hallway?
Absolutely.
So people are welcome to unmute for a couple of minutes and say hello?
And share their video and everything.
I cannot start my video because the host has stopped it.
You should now be able to start your video.
Nope. Well, we can fool around with Zoom controls for 3 more minutes and then start the next talk.
You can fool around with Zoom controls for an unbounded length of time.
I just said ask to start video next to your name. So not sure what else I can do.
I think it's actually a bit unfriendly to just chat in Zoom because most of our participants are off somewhere else.
Well, if one thinks of this as a hallway.
But most of our participants are not allowed in this hallway.
Well, that is regrettably true. We have 128 participants in the other hallway.
Have no way to talk, do they?
That's very quiet, Ian.
They have no way to talk, do they?
No.
They can just watch. I do think it would be useful to reiterate, and I'm not sure of all of them, the various ways one might connect and ask questions, because we have people coming from different regions and whose methods for getting in contact with us are different. It took me a while to find the chat on the questions on Slack, for example.
The one way to ask questions is via questions on Slack. That's PLDI doctrine. So YouTube questions have been turned off so that we have a single source.
Everybody registered can get to the Slack channel, which is good.
Everyone who registered for PLDI should have been auto-added to the Slack channel. What might be slightly less obvious is that Lennart has made a question, a thing
for each
talk.
Yeah, I followed the example of Dan, which is so it's the same on the main PLDI, that each talk has a separate thread. So there are a couple of discussions already following Joel's talks, actually emerging, by the way, now. And I already received a couple of additional requests for people to be added to this particular Slack channel, REMS-DeepSpec, and I can do that live. So if you drop me an email, if you're registered, I can do that.
Doesn't seem like anyone's using any of the hallway track applications at the moment. I'm looking everywhere.
Anyway, it's 5 past the hour, so I'll start the recording now again, and we can continue with the next talk. Okay, so our second talk in this session is by Jiyoung Shin, who's a research associate at Yale University, and we'll talk about compositional atomic distributed object specifications for distributed system verification. Thank you very much for your talk.
Okay, can you guys hear me well?
Yeah.
Okay, so hi, I'm Jiyoung Shin. Today I'm going to talk about atomic distributed object specifications that can facilitate verifying distributed system composition. This work is done in collaboration with my colleagues at Yale, Jiyoung Kim, Wolf Honore, and Zhang Xiao. So today distributed systems are used everywhere. When we're using our smartphone or even IoT devices, those systems are connected to distributed systems backend. And we're using large-scale web services every day. And cloud services, data processing engine, all falls into the category of distributed systems. A lot of people expect that distributed system will become the norm in the future. This is in part because Moore's law no longer holds, and applications are developing in a way that it can be highly parallelizable. Big data and AI application trends, serverless computing and disaggregated computing trends all points to the fact that distributed system will be used more and more in the future. However, distributed systems are known to be difficult to build correctly due to its inherent concurrency and weak failure assumptions. And what is worse is a subtle bug in distributed system can lead to huge consequences. For example, we often see in news that a subtle bug in distributed system leaking large amount of sensitive information or shutting down a large-scale web services or even an entire data center. Of course, software developers spend a lot of time to debug their software and also test their software, but these news show that software testing and debugging itself is not enough. Then what about software verification? Over the past few years, verification of distributed systems have shown great advances. For example, Iron Fleet suggests verifying functional correctness and protocol safety in isolation to easily verify distributed systems. Verdi suggests verifying distributed system under a strong network assumption easily, and then relaxing it into a relaxed network assumption environments. Wormspace suggests using reusable verified building blocks to build distributed system and verifying them. And there are a lot of approaches to reason about distributed system properties and safety in an automatic way. However, the bottom line is distributed system verification is still non-trivial. What makes the problem domain more complicated is that just verifying individual or standalone distributed system is not enough. In the real world, there are numerous distributed services and systems running already. And when system developers or application developers build application on top of distributed system, they not only use one distributed system, but commonly use multiple distributed systems to build their application. Also, it's a common practice to build large-scale distributed system based on smaller distributed systems, and same applies to multiple cloud services. Of course, there are existing work that tackles the problem of verifying composition of distributed system. For example, in Diesel, if you have verified distributed systems, you can reason about the safety of their interaction, and typically this reasoning is done at a network level. However, if we start reasoning about distributed system composition at the network level, we can easily verify small examples, but there can be some limitation in terms of scaling the verifiability. For example, a standalone distributed system can be already very complicated in terms of network connection. And if we have multiple of such systems that are interacting with each other, the message being passed around can be soon intractable. So the approach that I'm going to propose today is first coming up with the high-level model of individual system, which can be modeled as an object, and then reason about their interaction at the object level. Basically, this high-level model can obviate low-level reasoning, and this can potentially give us scalability in terms of reasoning about composite distributed systems. Of course, the low-level verification can be done using various techniques. In our project, we use certified concurrent abstraction layer approach to verify individual systems, but other verification approaches such as Ironfleet or Verde can be compatible with our high-level model. There is an added benefit for using a high-level model for verifying individual distributed systems. Although it may not have a very deep impact, approaching verification from top-down manner can provide some guidelines to verify a low-level system because the high-level model captures a common characteristic of various distributed systems. So the high-level model of distributed system that I'm going to propose today is called atomic distributed object. Atomic distributed object, or ADO, models strongly consistent replicated systems such as multiplexes, chain replication, and raft. Basically, ADO targets to model systems that satisfy replicated state safety, which can be informally defined as when there are multiple clients accessing the same distributed system, all clients see the common prefix of the committed states. This is a similar definition to the definition of linearizability. We want our atomic distributed object model to be as simple as possible so that we can reason about distributed system composition without worrying about protocol dependencies. So the high-level idea is if we have multiple distributed systems, we want to model individual system as atomic distributed object, and we want to reason about their composition without worrying about individual protocols. Then, aren't there any existing model that we can borrow to model individual distributed systems? And the closest model that we could find was a push-pull model that was used for concurrent shared memory reasoning. In this model, a persistent shared state is represented as list of state changes. And if a user wants to make modification to the shared state, the user must first pull the state into its local memory. Pooling operation gives ownership to the user. In this case, the blue user owns the persistent shared state. And if the blue user owns a persistent state, then all other users are blocked from accessing the shared state. In essence, the pool operation works similar to a lock. The blue user can continue updating the local state. And if you want to make the updates visible to all other users, the user has to first push the state into the persistent shared state. Once the update is pushed to the shared state, then the ownership is released and the state is updated and all other users are free to access the shared state. Similarly, if the red user pulls the state, the blue user will be blocked. The red user can continue making updates, and then it can push its update to the shared state. This model is very simple and elegant, but there are some limitations in terms of modeling distributed system. Because in distributed systems, user cannot be completely blocked because users may exist in completely different nodes. Also in distributed system, there can be random network and node failures, and this is not reflected in this model. Also, because distributed system execute operation over multiple nodes, failed operation can leave some visible traces in some of the nodes. So by modifying the push-pull model to reflect these limitations, we're going to propose a new atomic distributed object model. then how can we handle the case where user cannot be blocked? In this case, we're going to allow preemption. For example, if in this model, the blue user wants to make changes to the state, it will first pull the shared state as in the previous model. The blue user can claim the ownership of the shared state and make local updates. However, in the meantime, if red user also wants to pull the shared state, it can freely do it. This pull operation will preempt the ownership of the shared state. And if that's the case, the blue user can no longer push its update to the shared state. However, red user can continue to update its local state. And as long as the ownership of the shared state still remains as a red user, then red user's update will be applied to the shared state, making the Q state, which is the shared state, to 2. Now I'm going to explain how we handle network and node failures. To handle network and node failures, we simply add non-determinism to each operation. So for example, if the blue user does a pull, the pull operation can succeed, or either it can non-deterministically fail, reflecting, for example, network failures. Now I'm going to explain how failed operation leaving visible traces can be modeled in this model. To model failed operation that leave visible traces, we add volatile cache state in addition to the persistent shared state. Volatile cache state is in the form of tree, where individual node represent failed visible traces of previous operations, and the edges of the tree represent some dependencies among these failed operations. Because of this volatile cache state, we need to modify the semantics of pull and push operation. For example, if the blue user does a pull on the entire state, we need to first be able to determine based on which state the blue user will start modifying the Q state. In this case, we allow blue user to non-deterministically select one of the volatile cache states. For example, if the non-determinism returns the root node, that means the blue user is starting to work based on the latest persistent state, which is Q state of 2. And if the blue user non-deterministically selected in Q state of 4, that means the blue user is working based on the persistent shared state plus the uncommitted update state of 4, meaning Q state will be 2 and 4. Now the blue user can continue working on its state and make local changes. In our atomic distributed object model, we model these local changes as method calls. Individual method calls will be directly reflected into the volatile cache tree, and the new update will be simply appended as a child node to your current working node. The blue node can continue working on updating its local Q state, and when it comes to time which the blue user wants to persist their update into the shared state, blue user will trigger the push operation. Push operation will first examine the entire branch that the blue user is working on, and again, non-deterministically select one of the nodes in the branch, and it will commit that node and all of its ancestor. In this case, in Q of 5 and in Q of 4 will be committed in order to the persistent shared state. Now that some of the nodes are moved to the persistent shared state, updating Q state to 2, 4, and 5, now we need to restructure the volatile cache tree. In this case, we simply attach the remaining nodes in the branch to the root, and we remove all the other branches. The reason for this is all the other branch no longer holds valid dependency towards persistent shared state, which was just committed. Basically, all these operations model the atomic distributed object model, and a lot of you might be wondering whether this indeed faithfully models distributed system, and you might be also wondering how this maps to distributed system operation. So I'm going to show you the same example side by side with an example implementation shown on the underlying figure. In the bottom figure, I'm showing a multi-paxos-like system, which consists of 5 nodes. Notice that the blue user is at node 1 and red user is at node 5. You'll notice the persistent shared state of the queue is currently 2. And in the bottom figure, you'll see all the nodes contains the state of 2, meaning that the state is safely committed in all nodes. In multi-paxos-like system, if you want to do any meaningful operation, you need to be able to communicate with majority of nodes, meaning 3 or more nodes in this setting. You'll notice in node 2 and in node 3, there are some uncommitted states that are not copied in all of the nodes. In node 2, it has a queue state of 2 and 4, and in node state, it has a state of 2 and 3. Notice this. These states are some of the failed traces in the previous operation, and these states are reflected in the volatile cache tree. Now I'm going to show you what pull and push operation really means in the higher level model and the underlying system. If the red user does a pull operation, and if this pull operation non-deterministically failed, that means in the underlying system, node 5 tried to pull the state from distributed nodes, but due to unseen network outage, this operation simply failed. If the red user successfully pulled the system state and non-deterministically selected the root node, that can mean something like the node 5 communicating with node 1 and node 4, but due to partial network failure, not with node 2 and 3, and only seeing the persisted state of 2. Now I'm going to explain what it means for a user to preempt other users' ownership of the system. Now, blue user tries to also concurrently access the shared distributed system. If the blue user succeeds to pull and non-deterministically selects in queue state of 4, that can mean that node 1, which is the blue user, successfully communicated with all the nodes and seen the entire distributed system state. However, because the queue state of 2.4 is the latest state, which is represented as a time step on the right subscript, blue user chooses to use queue state of 2.4 as its base state for future operation. Let's say the blue user continues to do local updates. In queues 5, and locally, the queue state will become 2, 4, and 5 in the underlying system. And these operations are pending updates that are going to be sent over towards all the distributed system. Now the blue user tries to push its update. However, due to unseen network failure, this push operation can completely fail. However, blue user continues to make local changes and also accumulate more pending updates. Now, you'll notice that these update states are reflected in volatile cache state. This is because in the meantime, if other user tries to pull the entire system state and somehow contacts node 1, these pending updates will be visible to other users as well. If the blue user tries to push its state in the atomic distributed object model, we select a random node and its prefix and persist it into the persistent shared state. This operation can be explained as follows. In strongly consistent system, pending updates are updated and sent to the nodes in strict order. So in the underlying system, we first commit the queue state of 2.4, and then next, the blue user will try to commit the new state of 2, 4, and 5. However, due to unseen failure, maybe the update of queue state to 2, 4, 5, and 6 only partially succeeded. Now the ADO model's tree structure is reorganized, and the result of the underlying system looks as follows. And you'll notice that at node 5 and node 3, there are some states that are not reflected in the ADO model on the top figure. For example, queue state of 2 in node 5 and queue state of 2, 3 in node 3 is not found in the top level figure. The reason for this is in Paxos-like system, you need to, again, contact the majority of nodes. And if you select any of the 3 or more nodes in the system, the only state you can get is Q state of 2, 4, 5, or 2, 4, 5, and 6, which are only represented in the higher level figure. So the ADO model is hiding unnecessary details that are not necessary for system state reasoning. So overall, to summarize how atomic distributed object model works, it uses non-determinism to model low-level network and node failures, and it uses persistent state to model an ordered list of consistent updates, and it uses volatile cache tree to represent partially successful state, and the edges represent the state dependency among these failed operations. Then, why would we want to use ADO? ADO looks pretty simple, and there should be a good reason to use this for reasoning about distributed system. The first reason to use atomic distributed object is that the ADO behavior maps well to distributed protocols. Atomic distributed object is a logical construct, and it can map to any underlying implementation, regardless of its using a log like Paxos or Raft, or system that does in-place update like primary backup. For example, the ADO's pull and push operation maps well with Paxos family's prepare and accept, and Raft family's request, quote, and append entries. And also it maps well with chain replications, read from tail, and writing to head, and propagating its right. We believe ADO captures the common high-level characteristics of most strongly consistent replicated system, and it facilitates refinement proofs. Indeed, we have verified the replicated safety of Paxos family and chain replication, and we've shown that these Paxos variants and chain replication all refines the atomic distributed object model. We're also currently working on showing that Verdi-Raft proof that has been done by University of Washington also matches the ADO model. The second reason to use atomic distributed object is it can be safely and easily converted to a deterministic model when it comes to distributed system composition. When developers work on building large-scale application that uses multiple distributed systems, typically the non-determinism and failures that I showed you in the earlier slides are hidden under higher level APIs. The API repeatedly retries this non-deterministic operation until it gets a deterministic answer. We can mimic such behavior using ADO API. For example, we can first retry pull until pull succeeds, and then we can call method, and then we can push until the method call is committed. Notice that this loop operation only uses ADO APIs, and the safety of this operation is guaranteed by our proof. Therefore, we assume deterministic method call model for ADO composition in the examples coming in the next slides. Once we have the ADO model, how can we use this ADO instance? ADO can be instantiated into any data structure because it's a simple object. You can instantiate it into counter, queue, stack, list, or array, and so forth. More interestingly, we can instantiate ADO into higher level constructs such as log, file system, key value store, and so forth. For example, an ADO array can look something like this. We can first define the shared state as a map, and we can write a write function such that it updates the corresponding index with the given value. Similarly, we can also design a log based on ADO. We can simply define a map and a tail pointer of the log, and the append operation will update the tail pointer, save the new value at the tail of the log, and return the saved position to the user. More interestingly, we can also design a log based on atomic distributed object. To do that, we simply define an integer that points to the owner of the log. Acquire log can simply check whether the caller is the owner or whether nobody holds the log. If that's the case, we can update the current owner to the user. Releasing log can be designed similarly. We can simply check the current owner, and if the caller is the owner, we can change the owner pointer to bottom. A more interesting and practical example of atomic distributed object would be key value store. We can define a key value store by defining a shared map structure, which stores the value and the size of the value which correspond to the metadata. The put operation can be simply designed as updating the corresponding key with the value and the metadata, which is the size. However, in a realistic setting, if you want to really build a scalable key value store, oftentimes you want to have separate storage system for the data and metadata. And at the same time, if you want to synchronize the metadata and data storage, you may also want to have some synchronization primitives such as a lock. So we can use 3 distinct ADOs to construct a same function in key value store, which we call key value store lock. The design of key value store lock is simply reusing the low-level ADO construct. For example, we can use a lock and array that I introduced in the earlier slide and define lock, data, and metadata store. The put operation will simply first acquire the lock, write to the data, write to the metadata, and then release the lock. However, you'll notice that if the user crashes while holding the lock, the liveness of the system won't be guaranteed. So unless you want to put some additional mechanism to guarantee liveness, you can also think of a lock-free design of a key value store. We can simply have data and metadata ADO and come up with the key value store with no lock. In this design, instead of an array, we're using a log to store the data and using the array structure to store the metadata. The put operation will simply append the new updated value into the log, and it will get the returned index. And then it will write the size of the value and the data location into the metadata storage. You'll notice that even though the user crashes right after appending the data, the metadata storage will still point to the older data, and the consistency won't be harmed in the entire system. Overall, these 3 different key value stores are seemingly non-distributed code, and verifying the equivalence of these compositional key value store with a singular key value store can be done in a very simple fashion. Another nice thing and the benefit of using atomic distributed object is such compositional reasoning can be completely separated from choosing the low-level implementation. For example, if we want our synchronization primitive, which is a lock, to be highly available, we can choose to back it up with multi-paxos implementation. Again, if we want our metadata storage to be highly available, we can use different replication protocol like RAF to back it up. And for example, if we want high throughput data access, and if we want our data storage to be having higher throughput, we can use chain replication as its backing up protocol. But these decisions can be completely independently made out of this compositional reasoning. So based on this atomic distributed object model, we created a verification framework called advert. At the center of advert, there is this atomic distributed object model. However, because ADO is fairly high-level abstract model, there are some difficulties in terms of connecting this model to the low-level implementation. So we created an intermediate specification, which we call the network-based specification. Network-based specification is parameterized specification that describes the network-level behavior of certain family of protocols. For example, we created a network-based specification for Paxos-like network patterns. We've shown that this network-based specification faithfully refines the atomic distributed object model, and this refinement proof can be reused to verify low-level system implementations. Under the network-based specification, we can have concrete system specification. For example, we can write multi-Paxos specification and connect it to the network-based spec. Because it's a simple instance of the network-based specification, we only need to do very simple invariant proof to connect our multi-Paxos specification all the way up to the ADO model. If you have a corresponding C code implementation, we can also connect it to the system specification using certified concurrent abstraction layer approach. Similarly, we can instantiate and verify other Paxos variants, such as single degree Paxos, vertical Paxos, and so forth. Of course, atomic distributed object is not only limited to Paxos variant. Like I showed you earlier, we can also deal with strongly consistent primary backup protocols, such as chain replication, we have verified the refinement relation to ADO, and we're also working on proving Raft. Once the full stack up to the ADO is verified, we can simply use the ADO model to reason about higher level composition of distributed system, again, without having to worry about the low level details at all. I'm going to briefly show you how our adverse system is implemented and show you the evaluation and conclude the talk. The specification for atomic distributed object model looks something like this. The main state in atomic distributed object is a list of updates, which is reflected in the persistent memory state. And we have a cache tree, which represent the volatile state and the failed operation. Notice that because the persistent memory is a simple list that evolves in an append-only manner, verifying replicated state safety is very easy in the ADO level. Underneath the ADO model, we have a network-based specification, and the network-based specification looks something like this. If you want to verify the refinement relation, we need to first find the matching state in the atomic distributed object and in the network-based specification. The main state in network-based specification is a log of network events. These network events can be replayed using network replay function, and then the network replay function can generate individual node states in the distributed system. Because the states are scattered around different nodes, we can also use quorum check-like function to consolidate the state into a similar state to the atomic distributed object. The state update function looks like the one that just popped up. The push operation needs to work based on non-determinism. So every operation in atomic distributed object consults a oracle to get non-deterministic answer. A corresponding function call in network-based specification like Paxos to push is a commit or accept operation. In this operation, Paxos protocol will broadcast a request and then wait to get majority replies from all the other nodes. Also, these network operations involve non-determinism, so we have a network oracle that gives non-deterministic answer. Based on these similarities, we were able to verify the refinement relation between network-based specification and the atomic distributed object. Notice that in the network-based specification, there are few variables and functions that do not have concrete instantiation. These are parameterized and they can be instantiated to concrete Paxos variant protocols. For example, by instantiating the state to single immutable value, we were able to model single degree Paxos. By using the log as a state, we were able to model multi-Paxos and vertical Paxos. And by instantiating the state to an arbitrary in-place updatable object, we were able to model cast Paxos. Of course, the corresponding method called to update these states and quorum checks can differ from protocol to protocol. And because these instantiation needs to be verified to be connected to the higher level model, we have to do simple invariant proofs, such as quorum intersection properties and so forth. And of course, because the network-based specification is already proven to refine the high-level ADO model, the refinement proof for all these lower-level protocol can use this refinement proof between the network-based spec and the ADO model. Overall, the advert system is implemented in COG, and this table summarizes the proof effort and specification effort that was put into this project. Overall, the baseline advert specification and common library for refinement proof constitutes 13K lines of code. And based on this code, we were able to verify the Paxos-like specification and ADO's refinement relation using 5K lines of code. And we were able to verify the refinement relation between chain replication and ADO using 2K lines of code. Overall, these lines of code show that ADO refinement proof is not too trivial. However, these proofs show that ADO model is fairly general and it can model various protocols like Paxos and chain replication. However, once this complicated refinement proofs are done, verifying individual protocols such as single Paxos, multi-Paxos, vertical Paxos, and cast Paxos was fairly easy. Individual protocols were proven with only 500 lines of code or less. The best thing about the ADO model and advert is that compositional distributed system reasoning is really simple. Specifying and verifying the equivalence of the 3 key value store example took only a few hundred lines of code. Connecting the C implementation to our advert or ADO model took 43K lines of code. This is a fairly large amount of code, but these proofs are pretty mechanical and tedious work. In our group, we're working on automating this C code verification using a deep C compiler. Overall, the advert project and atomic distributed object project is an ongoing work. So we have several future directions that we would like to pursue. For example, first, we would like to test whether ADO can be extended to model systems with different consistency models. For example, we want to test weak consistency or Byzantine consensus environment. I've shown you a key value store example. However, we also want to explore more sophisticated ADO composition patterns that are found in real world. Also, connecting other verification framework to advert is also one of the list of work that we're trying to do. Like I said, we're working on connecting VertiRASP proof to our ADO model. To summarize my talk, I've proposed atomic distributed object as a high-level model that captures a common distributed system behavior. ADO model uses non-deterministic operations and uses volatile cache tree to model distributed system characteristics. When it comes to distributed system composition, atomic distributed object hides the low-level details of the system and allows for simple composition reasoning. When it comes to individual distributed system verification, ADO and the top-down approach of verifying distributed system allows us to come up with the middle-level specification that provides proof template-like specification that allows for easy verification of individual systems. So this concludes my talk, and I'll take questions. Thank you.
Okay, thank you very much. We have 4 questions at present on Slack, so I think we can probably go through all of them. So the first one is by Claire Young. This might be a silly question, but when the node pulls the queue, will local state be ignored in case of a conflict?
I'm not quite sure what conflict means, but basically the pull operation is similar to reading the distributed system state. So if your local state holds a older state that is obsolete, then pulling the distributed system state will basically overwrite your old state and maybe ignore the old state and use the new pull state as your base state. Yes.
Okay. Second question, Andrew Appel. For proving the implementation of C code, can you use other C verification frameworks beside CCAL?
Yes, yes. We believe that should be possible. So basically, above the CCAL verification level, we define the high-level specification of the system. So basically, the top-level specification of the verified C code only needs to match with the system specification in between. So any C verification tool can be used.
Okay, thank you. Next question by Ji-Hong Kang. Is advert capable of verifying high?
Preserve the replicated state safety. Basically, at the core of advert, there is atomic distributed object, and it's a fairly logical and high-level model, so it can map with any implementation of distributed systems. Of course, if you want to verify a production quality system, which involves a lot of optimization and extra operations that needs to be verified, then maybe verifying such small modules and properties might be something that needs to be done in a tedious way. But the high-level safety property of such system can be verified and captured in advert and the atomic distributed object model.
All right, the next question, I believe you briefly hinted on that topic already, is by Gilliard Posluns. How would you model a system with relaxed consistency guarantees using the ADO model?
So basically, that's one of our future direction. Of course, the ADO model itself models strongly consistent systems, so it cannot be directly applied to weakly consistent system, because weakly consistent system tend to not preserve the strict order that is enforced in our ADO model. So this is really a future direction that we would like to explore. Basically, modeling weakly consistent system will involve tweaking the persistent state as well as the cache tree so that we can model those weakly consistent behaviors.
Okay, thank you. And in fact, one more question emerged over the last 2 minutes by Elliot Moss. Question, if you have operations that are commutative, can you improve performance? For example, allow more commits, pushes to succeed by allowing those operations to commute as they are added to the underlying state?
That's an interesting question. Basically, again, atomic distributed object is a logical construct. So if you have a commutative operation, maybe like the intermediate type of all those commutative operations can be logically captured in the ADO model. In terms of optimizing the performance, if you're talking about the system performance, then maybe that can be done independently from the ADO or advert. But definitely, commutative model can maybe simplify the reasoning of composition. You'll notice that in our compositional model, we're using a deterministic model, and in the deterministic model, we're using an idempotent function to make some deterministic answer from the repeated operation. And maybe introducing or assuming most of the operations are commutative can maybe simplify that repetitive execution model in a simpler way.
Okay, thank you very much. No more questions, but I'm sure there will be more discussions on the Slack channel. I see that for the previous talk, there was lots of discussion over the last 20 minutes or so. So thank you for all the participants on that. And with that, I'd like to thank again both speakers of the first session. And we'll reassemble in about 11 minutes on the top of the hour for our next session. Thank you very much.
I think I'm next, so I'll try to share my screen and make sure it all works. Can people see those slides?
I can see the slides fine.
Okay, good.
Okay, let's start up again. Leonard, do you have your finger on the record button?
Yep, just started.
And Alistair, take it away.
Okay, so I hope you can all hear me fine. I'm going to be talking about Sail, which is a language we've been working on in Cambridge and some other places for quite a while now. So you'll see this sort of giant list of collaborators. We have some people, most people from University of Cambridge, but we have Brian Campbell and Ian Stark from University of Edinburgh. We have Prashant from SRI and Alistair Reid, who was at ARM, who's now at Google. So I apologize if some of you have kind of seen some of this talk before, because I've given a talk about Sail a couple of times. So the first half of the slide, if you've seen me talk about Sail before, you might have seen some of these slides. But the second half of the talk, I'm going to talk about some more recent work I've been doing. So I'm going to be talking about some work on symbolic execution and axiomatic concurrency models and sort of how we can support those in Sail. So to get started, just to sort of set the scene, so we're talking about specifying instruction set architectures. So these instruction set architectures, what they're specifying essentially is the interface that the hardware gives to the programmer. And if we want to specify these, well, I've got this picture that I rather like putting in all my talks, which is a picture of all the Intel 64 and IA32 architecture software developers manual, right? So you might think that instruction set architectures, well, they're really simple, right? They just specify, you know, some instructions like add and subtract and jump and whatever. It's really straightforward and there's no complexity here. But then you look at these manuals and they're like 5,000 pages or, you know, multiple volumes. And the problem isn't just that these things are really big, it's that they're all written in this sort of mixture of prose and pseudocode. So you in the Intel manual, there's sort of pseudocode for each instruction, but then that's not the whole picture. You then have to read the text, and the text may contain sort of extra little things that you have to bear in mind. And you know, as with anything that's sort of written in prose, you end up with things being sort of loosely worded, maybe even containing errors, right? Because if it's just a prose document, it's not sort of an executable test oracle, then you know, you have no way of really knowing whether it's correct. There might be subtle errors can creep in if things are not sort of tested. And you know, if you don't have a machine readable specification, if this is kind of what you have, you know, things that people are interested in this community, like doing machine check proofs or just testing and verifying implementations against a sort of rigorous specification, it just isn't possible. So, you know, I don't want to claim that our work on Sail is like the only game in town, right? You know, people have been doing formal instruction set architecture models for quite a long time. So this is just a small sample of kind of projects in this area, right? So you have things like CakeML, which has sort of multiple backend models specified in whole. Of course, CompCert has its own x86 model, I think models for other architectures as well. Then again, you have SEL4, where they have a model that was written by Anthony Fox in Hull, or L3 for ARM v7, and you know, like I said, many, many more. So the thing with these models is, in general, either they're kind of tied to a specific use case and tool. So if you look at, say, CompCert, then their x86 model is very focused on, like, at least this is my understanding, is that it's the sort of set of the ISA that you need to support a C compiler, right? So C compilers aren't going to use every instruction in the architecture. They're going to use some subset of the architecture, and there's some weird corners of the architecture that probably isn't going to be touched by the C compiler. And on the other side of things, you often have models, and this kind of ties into that, where you don't have system-level features. So what I mean by system-level features is if you were writing some system software, like a hypervisor, you might be interacting with the page tables or other aspects of the architecture that, like, a model for a C compiler just wouldn't care about because it's just sort of outside the scope of the C abstract machine, right? So stepping back from that, so our solution or our way of specifying instruction set architectures is with this language called Sail. So I'm going to briefly describe sort of what SAIL is, and then I'm going to talk about sort of our specifications and where they come from, how we wrote them, and kind of what's going on with both ARM and RISC-V, which are kind of the two main specifications we've sort of been focusing most of our effort on. So SAIL is it's pretty simple, we hope, imperative first-order language for instruction set architecture specification, and it has lightweight dependent types for bit vectors, which we check automatically using Z3. So you don't need to do any kind of manual proofs with these types. And we sort of first created this language to specify instruction set architectures for concurrency models. So there's going to be a lot more detail about that in the next talk by Christopher and Shaked. They're going to talk a lot about concurrency models and modeling concurrency and all the stuff that goes on there. But I have this sort of example to kind of demonstrate sort of just very quickly what it looks like and what these kind of dependent types let you do. So you might have, say, a function called getWidth. So you can imagine lots of architectures where you have a split between 32-bit mode and 64-bit mode. So, we might call this and we can assign it to some variable, which has a tick because it's sort of a type level variable as well as a runtime variable. So there's a bit of ML sort of heritage going on there. And then I can create a bit vector called wise, which has the length of the value returned by this function. And then we also have some flow sensitive typing. So I could say, well, if the length of this y is 32, then I can, I have this magical like special built-in, which I can ask the type checker within this if statement to prove some type level constraint. And it's going to say like, yeah, this is always true. So the idea is to have this kind of very simple imperative semantics of the architecture, which is often how, if you look in the architecture manuals of the pseudocode, they're usually specified in this kind of simple imperative style, right? And one of the nice things about this simple imperative style, where you have, no aliasing, no pointers, and none of the kind of complexity that you get with kind of a real programming language, is you end up with something that's very amenable to static analysis. And I'll sort of come on to sort of how we've exploited that fact later. And one of the things we do, because we started off caring a lot about concurrency, is the behavior of the memory actions we sort of leave to an external memory model. So there's sort of an interface by which these models can sort of interact with a separate concurrency, and we sort of plug in different semantics for that. So again, I just give another example. Sort of here's sort of a simple RISC-V instruction. And one of the little features we have is we can split functions up. So we have an execute function which executes instructions, but we can say that this is only a single clause of the execute instruction. And it's executing this kind of I-type instruction in RISC-V, which is going to be either an add immediate or an and immediate or an or immediate or an XOR immediate. And not just executing the instructions, but our specifications also include some code for doing the encoding and decoding and doing assembly and disassembly, although the assembly and disassembly is a little bit limited because it only really works for single instructions. So if you want to do more complicated things, you kind of need to use a real assembler. But these are also bidirectional as well. So there's some syntax for specifying functions in a bidirectional way. So this sort of mapping, these arrows you see kind of, they go both ways. So you can go from the binary to this enumeration, or you can go from the enumeration to the binary encoding. There's just a more concise way of specifying these things. So what's the overall sort of picture? Why do we even have this SAIL language in the first place? Well, one of the reasons to have it is, we have all these different instruction set architectures. So we have ARM, we have RISC-V, we have MIPS. In the past, we've done some stuff with Power and x86, but we haven't really focused on them recently, which is why they're kind of grayed out here. And at Cambridge, we're sort of very interested in these cherry capability architectures. I think there's going to be a talk on sort of cherry and cherry verification tomorrow. So we have lots of architectures, and then we have lots of things we want to do with all these architectures. So we generate emulators for testing. We can also generate tests themselves. So Brian Campbell and some of our collaborators in Edinburgh have done work on test generation. We also want to do some kind of automatic verification, which is either via sort of SMT solvers, or we have this ILA axiomatic concurrency tool, which I'll get to later, and sort of symbolic execution. And then, of course, all the theorem provers. It might be heresy to suggest that there are other theorem provers other than Coq in certain circles, but we do want to support theorem provers like Hall4 and Isabelle as well as Coq. So we're kind of trying to support all the common theorem provers that different projects are using. And then we also have this RMM tool, which is for operational concurrency. So having this language it kind of sits in the middle and solves this kind of many-to-many problem between all these architectures and all these different use cases. That's kind of one of the main advantages of it. So just to briefly cover kind of what models we have. So we have models for ARM v8, 5, MIPS, Cherry MIPS, RISC-V, and Cherry MIPS. So then there's so we've recently been working on this Cherry extension of the ARM architecture, which is called Morello, and there's like a digital security by design kind of grant in the UK, which is focused on sort of capabilities and this Morello architecture. And it's sort of in progress at the moment. So the exact size of it is not completely clear yet. But you see the ARM architecture, we translated it automatically from the ARM specification language called ASL. So it's kind of really huge. And I think some of these numbers may actually be slightly outdated now. But sort of the key thing is that for the architectures where we're most interested in them, they're all sort of complete enough for system software. And one of the ways we validated that was, trying out booting operating systems on them or running hypervisors. So there's this Hafnium hypervisor being developed by Google, and we've sort of run that on top of our ARM model to test a little bit of the hypervisor mode support. And the same thing for RISC-V. So trying running FreeBSD, Linux, FreeRTOS, Hafnium on top of RISC-V. So just talk about our RISC-V specification just briefly. So, I'm sure most people here know what RISC-V is, but it's sort of an open instruction set architecture. It's kind of being developed by a broad industrial and academic community. So what we've done, we've specified, I think, most of the base architecture and the common extensions, and we've validated it against the RISC-V conformance tests. We've done trace comparison with a spike simulator. And doing this kind of formal work, one of the nice things is if you can, collaborate with the systems people developing it, you kind of get this nice sort of feedback loop where your work formalizing it you can discover bugs or small imprecisions in kind of the pro spec, and it kind of leads to this nice virtual cycle. So we found some issues with descriptions of page faults and page table walks, some ambiguities in interrupt delegation and so on, and some bugs in kind of the spike simulator. And we have some integration with this RISC-V model into the RMM operational concurrency tool. So we can test sort of the concurrency litmus behavior of the architecture. And there was sort of a RISC-V formal working group, and the SAIL model got selected as kind of the official RISC-V formal ISA model. Although it's still not fully, there's still some issues with the full adoption, I think, there. But in principle, we were kind of involved in that formal group progress. So what about ARM v8? So this is kind of the other main architecture where it's kind of focused on a lot. So in this case, we had basically a language within ARM called ASL, which is their sort of executable pseudocode language. So it started off as just being pseudocode, but then they, Alistair Reed in particular within ARM sort of led an effort to have it become more executable and turn it into a real executable specification. So this is used within ARM for documentation, hardware validation, architecture design, etc. So the nice thing about this model is it's really an authoritative vendor-supplied semantics, right? So what we did here is we didn't want to re-implement it ourselves. We have a tool called ASL to SAIL, which translates ASL into SAIL. And ASL and SAIL are very similar languages. They both have, they're both simple imperative languages. They actually both have some simple dependent types for bit vector lengths. So this is actually a very natural and relatively straightforward translation. There are a few tricky issues with the type systems not completely matching up, but other than that, you get a fairly idiomatic translation from ASL into SAIL. And because this is sort of the most authoritative model from ARM, is you get all these different features, sort of basically everything in the architecture, right? So floating point, address translation, all the vector instructions, pointer authentication, hypervisor, whatever. And this is really cool, from my perspective, because having this really complete architecture is just not something that's been publicly available for formal reasoning before. So I think that's really exciting for. And of course, we translated it. We wanted to do some validation. So because of our collaboration with Alistair Reed within ARM, we were able to have him run it on their internal test suite, which is the architecture validation suite, which isn't publicly available, but it was really helpful because we were able to get, I think, 99% something like that tests passing. There were like a few issues with like little corner cases. I think some of those have been fixed now, but of course, because it's not public and
Looks like Alistair's connection is lost.
can you hear me now?
Yes.
I just got disconnected. Sorry, so it just like dropped me from the Zoom call. I'll start screen sharing again. I don't know if you missed anything.
Scarcely.
Okay. So you should be able to see the slides again.
Yeah.
Okay, so yeah, one of the other things we did with the ARM model was we tried booting Linux on it, and which is kind of a useful sanity test. But I do want to say that running Linux actually only covers about 25% of the architecture, which is sort of interesting. So and that's ignoring all the vector instructions. We were like, okay, running the operating system isn't going to use vector instructions, so we kind of sliced them out and then was like, okay, well, what's the instruction coverage? And it's like only about 24%. So there's a lot of the architecture that isn't even covered during the Linux boot. Although, to be fair, this is only the boot process, so we didn't really run anything because we don't have any devices. So you can kind of boot Linux, run a simple user space program, but then without any devices, there's not too much you can do. We also tried running Linux underneath a hypervisor as well to kind of test that hypervisor mode. So it's just some stats for the specification. I won't go into too much detail. So all the 64-bit instructions are like 66,000 lines of code. There's like 4,000 instructions. It's about 561 registers in the architecture, 1,000 instructions roughly. That doesn't necessarily correspond exactly with the assembly mnemonics, but it's pretty close. And what we found was like each instruction performs about 800 or so calls to different auxiliary functions for doing things like checking the current exception level, and all sorts of little checks like that. So one of the things we did was, I'm not going to spend too much time on this, but we tried doing some proofs about it. So we did like a spec where we sort of proved a simplified characteristic of the address translation. So we sort of took the address translation, we're like, well, what does address translation do in just sort of user mode? And yeah, if you look at the address translation, it is the most complicated part of the model. There's about 9,000 lines of specification. So one of the things we did was, we took it, we simplified it, and we proved in our simplified version, sort of a nice purely functional characterization of address translation was equivalent under some of the ordinary assumptions you'd have if you were just running ordinary software in user space. But we are now working on full-scale proofs for Morello, which is this Cherry extension of ARM, and Cherry RISC-V, and I think Thomas will be giving a talk tomorrow, which will have all sorts of details about that work and sort of previous work in that area. So yeah, this was kind of the theorem we proved. Yeah, just that the simplified translation was equivalent to the full address translation under the kind of sensible assumptions that, user mode, no virtualization, translation tables are valid, the hardware is updating the translation tables, etc. We actually uncovered a few small bugs in the ASL specification. I think to do with like things like endianness reversal, which is sort of infinite bugs in these specifications if you get endianness wrong. So interactive proof is really great, but it is nice to have something more automatic. So one of the ways we do this is we have kind of a quick check like system where we can translate sale source into SMT problems, and then we can verify properties of sale functions. So we have this kind of property from Cherry RISC-V, which is if you get some capability bounds, or if you set some capability bounds and then you get the capability bounds, you get the same capability bounds that you set up to some precision, because the capabilities in the Cherry architecture, they're sort of compressed in this floating point-like format. So if you have a very large capability bound, there might be there's some sort of maximum precision where you can represent things. So what happens here is you just write this property in front of any kind of Boolean function, and it'll generate SMT and it'll prove it automatically for you. So it's like quick check in kind of the workflow, but it is actually proving the properties and not just testing them. So the way this works is pretty standard. You go from sale to some SSA-based intermediate representation, do some simple symbolic execution and partial evaluation to get some simplified intermediate representation, and then you just turn that into sort of SMT constraints. So then we sort of, once we had this, I started looking at, how can we do axiomatic concurrency semantics? Because if we're interested in instruction set architectures, one of the things we want to be able to handle is, all processors nowadays, they're all multi-core. There's all this kind of interesting weak memory behavior, and our specifications should be able to support that. So we sort of thought like, okay, well, we can use this SMT-based infrastructure to test these litmus tests, right? We can take the code from one thread, so say thread 0 in this little example, and thread 1, we can compile those to SMT. We can write some constraints about the memory accesses, and it'll tell us whether the executions are allowed or disallowed. Turns out that didn't really work very well because it just didn't scale beyond small properties. So when you have things like 5 or 6 instructions, and I already described how big the ARM spec was, and these were like ARM litmus tests. So the SMT that got generated just became really huge and unwieldy, and it didn't work very well. And there were certain like technical issues, things like alignment checks, where the SMT solver just wasn't very good at figuring those out. So basically you end up with lots of case splits. Is it aligned? Is it not aligned? If it's not aligned, then the load gets split. But in practice, it's always aligned, but the SMT solver can't simplify it. And yeah, that didn't work super well. But we do want to analyze these kind of tests. So here's just to describe this little example very briefly. So this example is showing like a sort of observable speculative execution. So here we have a thread that does 2 writes. And then this load here in thread 1, the first load, it reads from the second write. So it reads from Y and it gets the value 1. But after the branch, the second load in thread 1, that's reading from the initial state, despite the fact that the value it reads X was written in thread 0 before the write to Y. So you can see that it's done this second load, even though it hasn't done the branch yet. So it's sort of this sort of speculative execution, and you can observe this behavior on actual hardware. So, like I said, the concurrency semantics isn't in the SAIL instruction set architecture description, because that's really only expressing the sequential behavior of the instructions. And there are 2 ways to express these concurrency models. You can have an operational semantics, which is like having an abstract microarchitectural machine that describes the allowable speculation and so on in terms of sort of caches and buffers. Or you can have an axiomatic model, which is like a predicate on candidate executions, which is essentially a graph of memory events. And in our case, we actually have both approaches can be made executable. So we have this operational semantics in LEM that integrates into this RMM tool, which I think will be discussed in the next talk. And there are other tools like HERD and MemAlloy. But in terms of their support for the instruction set architecture, they generally hard code some subset of the instruction set architecture, or they might only consider like reads and writes and just work in terms of reads and writes. So the instruction set architecture support there is slightly more limited. So the problem we kind of wanted to solve is how can we compute the model allowed concurrency behavior with respect to any axiomatic model, with respect to any SAIL instruction set architecture semantics. And, because we have the entire semantics, we want to do this in terms of like interesting features in the architecture, things like self-modifying code, which, that comes up in things like JIT compilers. So, we're doing this on Zoom, so there's all sorts of like JavaScript and going on, which is, using a JIT and modifying its own code, and, that kind of stuff is interesting. So what we decided to do was to use symbolic execution of the SAIL source, or the sort of intermediate representation produced by SAIL, to build a tool similar to HERD, which takes sort of 3 inputs. So it takes a litmus file, which is one of these little tests that you saw on the previous slide, a SAIL model, so basically the entire SAIL model, and it takes as an axiomatic concurrency model. And you put all these things together, and it can run these tests for you. I should say there's a lot of sort of related work in this area. So of course there's HERD, which I've mentioned. There's this D'Artagnan tool, which I probably butchered the pronunciation. Cerberus has a bounded model checking mode. There's a CLI has, I think at the last, I can't remember where it was, but there's a sort of CLI native, which is sort of machine code support for CLI. There's work being done by Daniel Perennial on CBMC, and yeah, there's all sorts. Like, this isn't even exhaustive. So we have this tool called ILA, which I briefly mentioned earlier, and you can see that the name is a sort of acronym for sale, or rearranging the letters. So this is a symbolic execution tool or library for sales specifications, and it's a sort of SMT-based symbolic executor for the intermediate representation that sale produces, which is for us a very simple go-to language. And this just isn't just useful for axiomatic concurrency, I should say. This is we can generate sort of simplified instruction summaries, which you'll see on the next couple of slides. Colleagues in Edinburgh are, again, applying this to do sort of interesting test generation for ARM. And this is available open source on this GitHub link, and there'll be some other links at the end of the talk as well. So let's consider the add instruction, right? So the add instruction is like the simplest instruction. So we want to think for a second, like, well, how is this expressed in the sales specification? Okay, so you have, well, you don't really have an add instruction. This code gives you an add sub instruction. So it's add and subtract. And in ARM, you have the add instruction, ADD, but you also have the ADC instruction, which is add with carry. So add won't set any flags, but ADC will. So this pseudocode in the ARM spec, which is translated into sale, is telling you how to do the add instruction, the add with carry instruction, the subtract instruction, and the subtract with carry instruction. So it's kind of 4 things all rolled into one, right? So you can see here that it's testing, like, is it a subtract op? Well, if it's a subtract op, we're going to invert the second operand, and we're going to set this carry flag. Then we're going to do an add with carry, and actually all the interesting stuff is kind of happening in the add with carry instruction. Because what that's going to do is it's going to do a signed sum and an unsigned sum, and it's going to like look at the difference between the signed sum and the unsigned sum to figure out, like, okay, well, do I need to set the C flag and the V flag and so on and so forth? And this isn't the entire spec, right? Because on top of that, you also have to decode the instruction, and the decoder is going to say, like, you know, I'm going to match on this shift and set the immediate, shift it, whatever, you know, all this extra stuff. So, and this is the add instruction, right? The load store instructions, they're way longer. Like, this is tiny. This is like this miniest, smallest instruction. But if you want to like reason about a single instruction, like you want to reason about all that complexity the whole time, right? So what the symbolic execution lets you do is it lets you take that instruction and it lets you just simplify it all the way down to basically what it does. So, you know, if you run ILA, which is our symbolic execution tool, on this instruction, you're going to get something that looks like this in kind of SMT-lib language. So it's going to, you know, read some register into some input value. It's going to 0 extend it because it needs to check these high bits for these flags. And then it's going to basically write that out to the output register R4. So then you can see, well, we're doing the add instruction. So if you apply some kind of simple rewrites, you can ask Z3 to do this, or you can write a little simplifier by hand. Because we're not setting the flags, this isn't the ADC instruction, this is the add instruction. This is actually equivalent to just adding 1. So add x3 to 1 is just adding x3 to 1. So all that sort of complexity in the pseudocode is just boiled down to sort of exactly what this instruction does. And this is very useful because now we can go from a you know, this really complicated semantics to very simple SMT for each instruction. So we can now apply this to the sequences of instructions we see in litmus tests. And then we can combine that with a translator for a subset of the kind of herd cat language into SMT constraint between all the reads and the writes in the test. So we have an online tool, which is kind of running on a fairly wimpy server. So if everyone watching this goes and visits it, it might crash. We'll see, because most of the processing happens server side, but hopefully it doesn't die. So because it might die, I got a picture on this slide. So this is kind of what it looks like. So you can see here in the top left, you specify the test in some sort of input format, where you can see here, this is like a simple message passing test. So we have, you know, 2 stores and 2 loads. And then we specify the memory model in this pane in the middle. So this is just a cat file. This is essentially, this is just basically copied from herd. Then I make a few simplifications for some features that I don't support because they're hard to translate into SMT. And then, you push this green run button at the top, and if the test is allowed, it'll generate like a graph, and graph is, which shows you whether the execution is allowed or not. And behind the scenes, it's compiling it into like an actual like ELF binary that it's then running in the model. So one of the nice things about this is because we have such a complete semantics, you kind of get all these interesting features for free. So things like self-modifying code. We had a paper at ESOP where we had a bunch of tests for ARM, which were sort of, and this is going to be covered in the next talk as well, I think, so I didn't want to go into too much details in this talk. But we had tests that were looking at like, well, if you have code that modifies itself and you have like instruction cache maintenance instructions, like what relaxed memory behaviors are allowed there. And these kind of, like I mentioned earlier with the kind of JavaScript JIT example, these interactions that, are often aren't thought about in this kind of work, but they can be very important for systems code. So if you look at the Linux source code, there's a whole bunch of places where it modifies itself, right? And lots of tools just don't even think about that, like, oh, self-modifying code, that's pretty scary, but like it happens in the real world. So it's interesting to think about. And because our tool, it just works with the full architecture specification from ARM. So you just feed it the, essentially the ARM spec translated into SAIL. So it just handles self-modifying code just like out of the box, because all the instruction fetches, they actually happen like in the spec. So you just have to make like an axiomatic model that can talk about that, and the tool just supports it, which is really cool, really nice. Yeah, and sort of this work on axiomatic concurrency is sort of joint work with a bunch of different people from the talk, the sort of title slide. And yeah, there's going to be a lot more detail about that in the next talk. Okay, so hopefully we'll have some time for questions, but to conclude, so we have these sort of hopefully rigorous semantics for real production architectures, and we've tried to make sure that they're usable for interactive proof. Interactive proof with all sorts of system features about interesting like operating systems code. We've built a symbolic execution tool for exploring the relaxed memory behaviors of these specifications with axiomatic descriptions of memory models. And the thing we hope is that by doing this work on specifying these instruction set architectures and trying to be as detailed as possible, is that there's lots of like exciting projects that other people can do that are sort of enabled by this work. That's kind of one of our hopes. So here's a whole bunch of links, and yeah, I think I have time for questions.
Okay, thank you very much. So we have several questions, also some answers, but let's start with the first question. Despite the Slack answers, Andrew Appel asks, you have a generic connection to COC, but can you connect specifically to concert specs for x86, ARM, RISC-V, etc.?
So I think so we can generate a COC semantics of our specification, but we're not connecting to like another specification. So if you specified x86 in SAIL, you could generate a COC specification for x86. But if say concert already has an x86 specification, then like we're not connecting to existing specifications. We're kind of generating our own. If that answers your question.
Yeah, let me add a bit more to that. So the concert ISA specifications, unless they've changed a lot recently, were very specific to concert. They were handling, just the instructions, and in some cases just the specific versions of the instructions that concert needed. So it would be a very worthwhile task to actually prove that that is a sound model above the SAIL specs for ARM and RISC-V, but that is not something that we have attempted to do.
Yeah, that's kind of a point I try to make, is that like if you're working on a C compiler like concert, then you only need to specify the subset that's used by the C compiler. So there's kind of different objectives going on there.
Yeah. Next question. So Ken Rowe, you mentioned that SMT solvers didn't work very well for verifying concurrency properties. Have you looked at other approaches? How much work would be involved in using an interactive prover like COC for those properties?
Oh, I meant, so when I said that SMT solvers don't work for verifying concurrency properties, what I meant was when we did the sort of the upfront translation. So we took all the sale and we translated all of it into SMT sort of upfront. So you end up with a huge SMT problem. And then there are some things that don't work very well. So you end up with, there's lots of little checks in the architecture for things like alignment, which means there's a lot of different branches and if statements in the SMT problem, which just explode the search space. So our SMT, our symbolic execution tool, is also based on using an SMT solver. But the thing is, because most of those things are statically determined, like that when you do the symbolic execution, you kind of know the alignment is sort of concrete, it's not symbolic. So the symbolic execution just kind of runs, and none of those details appear in the generated SMT. And once you get all that complexity out of the generated SMT, the SMT is just like the bare minimum for the instruction semantics. And then you have SMT for the axiomatic model, and you apply that, and then it works really well. So we have, like, for ARM, I don't know exactly how many litmus tests we have. We have lots of automatically generated ones using the kind of DIY7 test generator. So I think there's on the order of like 10,000, maybe more litmus tests. And if you grab like a pretty powerful like Xeon server, you can run all those tests in this symbolic execution tool in like 4 minutes across like 72 threads or whatever. So it's actually pretty fast, and the SMT solver is pretty fast. And there's only a very few tests that time out, like maybe 4 out of 10,000 or something.
Okay, Kenro also asked quickly, does the symbolic execution cover all cases?
So yes, at the moment, because we're interested in the litmus tests, like it kind of, in order to be sound, it has to cover every case. So at the moment, it doesn't like stop. If you have like a loop in your litmus test, it'll just run forever. Like it'll just keep going around that loop. And there's like a timeout where eventually it'll just fail.
Leonard asks, would something like Euler axiomatic in principle apply also to microarchitecture models along the lines of Margaret Martinozzi's group, where they have, axiomatic models relating abstract pipeline events and such like?
Yeah, I think it would actually, though I haven't thought about it too much. You'd have to have some way of axiomatizing those microarchitectural bits and pieces, but like in principle, there's nothing really stopping it from doing that. Just at the moment, we've been focusing on our architecture semantics. But kind of the IR, it doesn't really run on Sail. It runs on this very simple go-to language IR, and you can kind of axiomatize whatever you want in terms of that IR. So it would probably work with like a little bit of effort to add support for some of those features.
David Holland asks, how close is Euler or something like it to being a tool that you could use to verify properties of specific bits of assembly code against a specification?
I think you could almost just do that at the moment. It depends how long the assembly code is, but it can prove properties about bits of assembly code. So it's kind of set up as like a library in Rust, so you can sort of import it into your project, and you can set up like, I want to run this code and I want to check that it only ever does these things, and kind of use it like that rather than sort of as a push button tool, and kind of set things up how you need to specify properties, or check that things always hold in every intermediate step. So kind of anything you want like that.
Mario Carnero asks, is there a simple export format, e.g. S expressions, with a defined semantics for specs written in Sail?
There isn't, but there probably should be. It would be nice if OT could just generate one. So maybe that's a question for Peter. Because our grammar is written in OT, so.
It could if you wanted to define the semantics. But there's... Yeah. So there's work by Mark Wassel in Cambridge on fragments of Sail, some of which have defined semantics in Isabelle, which one could think of using. And you also might be interested in the Catamaran talk coming up tomorrow from various people. You might want, it depends on the purpose. So you might want to instead have defined semantics for one of the internal languages that SAIL uses on its way to generating theorem prover or C emulator code.
Yes, the intermediate representation I use for the symbolic execution is very simple, and it's very small, like semantics. Although it's not really formally written down anywhere, but it's super simple.
Yeah, so it depends on the purpose. If you don't want it to be, you know, human readable code, then that might actually just fit the bill. Sagar Jar asks, SAIL seems to be designed for ARM and RISC-V, which are RISC, so a number of complexities in the implementation are not necessary. I just have to interject there. The idea that ARM is RISC is still true in some sense, but it's not very RISC. Then he continues, with CISC architectures, you would have to deal with such issues like repeat prefixes on instructions. Do you think that would make it infeasible to use a similar approach for those ISAs, or would that just make the constraints a bit more complicated?
So we actually had a project student take the sort of Centaur ACL2 x86 model by Shilpi Gold and translate that into SAIL. And they were able to do that pretty successfully, I think. So I don't think there's any fundamental issues with x86. The only, like, you basically just have a more complicated decoding stage. Like, the decoder is a lot more complicated. And some of our things are set up, they kind of, they don't really assume a fixed size instruction, but it does make, having fixed size instructions does make things a little bit simpler, but like having a more complicated decode isn't the end of the world either. Like some idioms we use in our spec kind of wouldn't work so well, but yeah, there's no fundamental issue why you couldn't do x86.
Martin, yeah, I don't think it would make it doesn't make a terribly big difference really, as far as I can see. Although I say that without anyone having done a full x86 semantics, of course. Martin Berger adds to that, how far away do you think SAIL is from being able to do anything interesting about specifying GPU architecture?
So I know nothing about GPU architectures other than so one of the problems with GPUs is, well, I mean, part of the reason why I don't know anything is often the architecture for GPUs isn't very well specified, right? So if you want to program for a GPU, you're not really using an assembly language. You're talking to it either with like OpenGL or Vulkan or some other, and then, the GPU driver itself might have a shader compiler that's compiling compute shaders, and the compiler is like baked into the GPU. And this is like a whole world of craziness. And yeah, the GPU vendors aren't publishing documents that are like, this is the this is like the low-level instruction set architecture that we support. And with Vulkan, you kind of have this SPIRV or SPIRV, I don't know exactly how you say it, but that's a little bit closer to that, but it's still a little bit different from like an instruction set architecture. I mean, I know that the herd has support for like GPU concurrency, so you can specify like the GPU concurrency model kind of separately from like the GPU architecture. So that might be something interesting there, but yeah, GPUs they're kind of an odd world compared to CPUs, I think.
Yeah. Sagar wants to clarify the specific thing he was talking about for RISC and CISC was having direct memory-to-memory instructions.
You could write direct memory-to-memory instructions in SAIL. There's nothing stopping that.
In fact, in a sense, they already are, because they do many memory accesses as part of address translation.
Yeah, so in ARM, when you do like a single address access, then it accesses like possibly 4 levels of page tables. So there's a whole bunch of memory accesses that kind of really happen under the hood that you don't really see as part of the assembly language, but are kind of going on.
Samuel Gruter asks, are there any examples of cock proofs written against SAIL-generated cock specifications?
Yes, so I think Brian Campbell in Edinburgh has been working on doing some cock proofs. Although like we're mostly using Isabelle, so we haven't done a ton of work with cock, but yeah, there are a few.
Maybe if we should if Brian can turn on his audio, maybe he can answer it more concretely.
Hopefully my audio is now turned on.
Yep.
So I've ported some of Thomas's address translation proof but not all of it because we had some other priorities to work on. It's somewhat complicated because we went for quite a rich translation for Coq, and we also found it a little difficult to actually do some of the automation we'd like. But I can share those proofs if anyone's interested.
Okay, I think that brings us to the end of our questions. No more appear in the next 2 seconds. Then thank you very much, Alistair. So now we have...
Stop recording. I think we have 5 minutes time, right?
Yeah, so let us have a little pause or hallway conversation among those who can converse, and start again at 50 past the hour. You could all try turning on your video if you want to seem lively. I'd be curious to see if that works.
Doesn't work.
I've been told that the host has disabled it.
Can anyone see my screen?
We can see.
Yeah.
We can see the screen share, ARM-V8.
Yeah, and I assume you can hear me clear enough.
Yes.
Thank you.
Check it. Mind if I try the same?
Yeah, go ahead. Do I need to stop?
I don't actually know. No, yes, you do have to stop.
I stopped.
Okay. Let's see if that works. Can you see my my window?
This looks like ARM-V8 continued.
Continued, yes. Okay. Just I have to find out. Stop sharing. Yeah, thank you.
Okay, so next talk will be presented in a double act by Shaked Fleur and then Christopher Poulter. Leonard, have you got the recording?
I just started.
Yeah. So Shaked, take it away.
Can you hear me now?
Yeah.
Can anyone hear me? Okay.
Bit flaky, but yes.
So good morning. Oh, sorry about that. Good morning, good evening, good afternoon. I'm going to be talking with Christopher about the memory models of ARM v7 and RISC-V. This is a joint work with many people, as you can see. Some of them already appeared in the previous talk. As you might have seen in Peter's slide, architecture is the specification of the hardware and software interface. And here, particularly, we want to clarify the concurrent behavior that programmers can rely on. I'm going to start by giving a little bit of historical background, what we've been doing in the past 10 years to develop and simplify the ARM memory model. And then Christopher will take over and he will talk about more technical details of how we developed equivalent models in different styles. And he will give you tools that we've developed for those models. So early computers were single processors, obviously. They could be viewed as two separate subsystems. An execution unit that just executes instructions sequentially, and memory storage that records and replies for stores and reads. In practice, hardware needs to run fast, so hardware implements optimizations. For example, one of the more common optimizations is a store buffer. Instead of the thread having, instead of the execution unit having to wait for the memory to complete memory write instruction, the execution unit just places event in a buffer and continues, and it's the storage responsibility later on to drain the buffer into memory in its own time, maybe when the execution unit is executing some non-memory access instructions. And later on, when the execution unit needs to do a memory read, it just waits for the buffer to be emptied and then reads it for memory. Or alternatively, for slightly better behavior, faster behavior, it can just check the buffer and see if there is a appropriate memory write in the buffer and read it directly from the buffer. The point of all this is that even though the hardware is implemented in one way, to the program, the world still seems very simple. It's just sequential operations and nothing has changed. And then in the 70s, multiprocessor computers showed up. And the programmers still believe that the world is simple and look like that, while in the hardware, things look a bit differently. In '79, Lamport noticed that there's a little bit of a problem here. Multiprocessors behave not in the way that programmers expect. Lamport defines sequential consistency, which basically says that an execution is sequentially consistent if there exists some global order over all the memory access instructions of all threads that agrees with the internal order of each thread. So instructions from the same thread must appear in the global order in the same order that they appear in the thread itself. All the memory accesses are serialized one after the other in some order. So what does that mean? So let's look at a very simple pseudo-assembly program with two threads. And let's try to see what kind of a result we can get with sequentially consistent execution. So I'm starting by executing the first store of thread 0, and you can see that the memory now maps x, some arbitrary location, to 1. And I follow that with a load from y, which currently holds 0. So thread 0 reads 0. And then thread 1 performs another store to y this time. So y now changed its value. And then load from x, which sees x, which is 1. And this is a sequentially consistent execution, and it's all nice. But then we record the final state of this execution, which is both locations are 1, thread 0 saw 0, and thread 1 saw 1 when they loaded. But then what actually happens in hardware is a bit different. So we repeat the same program, some execution over a more complicated model. And here, when we perform the store now is placed inside the buffer and doesn't go directly into memory. When thread 0 does its load, it reads 0 from memory, just as before. Now, when thread 1 performs its store, it goes to the buffer again. And when it does a load, again, it comes from memory, and it is completely oblivious to the x equal 1 that appears in the buffer of thread 0. So later on, the buffers can see that we got a slightly different final state. Of course, the sequential execution could be repeated in different interleavings, but we will never get the same final state as we got with the buffers on the right. So this is an interesting execution. It's not sequentially consistent. We can make it more appropriate litmus test from it, where I extracted the variables to actually be held in registers. And that's basically how a litmus test looks. So some hardware optimizations are not sound with respect to sequential consistency. And we just throw them away. They are unsound. Unfortunately not. Single-threaded programs run much faster, and they have no ill effect, ignoring side channels, of course. Code of concurrent programs. It's only a small portion of concurrent code that behaves unexpectedly. So why can't hardware be implemented to be sound with respect to sequential consistency? Well, it just requires too much analysis of the code, which is not practical to implement, so they have to break it. Instead, they provide mechanisms such as instructions and dependencies to suppress those optimizations when we actually need it in the code. When we come to specify an architecture, we want it to be tight enough so we don't need to suppress those optimizations unnecessarily. And we also want it to be loose enough to include all reasonable implementations. So what is the state of architecture specification before 2010? We have reference manuals for ARM, Power, and x86, as you saw the picture from Alistair's talk. Those are quite big reference manuals. I calculated that the latest ARM reference manual would need 1.5 boxes of A4 paper to print out. Those reference manuals describe the pseudocode and they describe the instruction semantics in pseudocode with uninterpreted primitives over memory accesses. And the memory model, which we are interested here, describe the behavior of those memory accesses. Unfortunately, those are incomplete, ambiguous, and not formal. They're not usable as oracles or mechanized proofs. There were some exceptions, Spark, Alpha, and Itanium, which had quite good formal memory models still in text, so you would have to code them in Coq or something if you wanted to do anything with it. In 2009, Scott Owens and et al. published a model for x86, which turned out to be very similar to Spark, the TSO model. And then in 2010, Jad Al-Ghaib et al. Published an axiomatic memory model for power with some tools for systematically generating litmus tests, like the one we just saw. And then in 2011, Sassman-Stocker et al. Published the operational power memory model. So we have all those nice memory models. Can we use one of them for ARM? Turns out it's not so simple. Running litmus tests on ARM devices reveal that they behave slightly different from power. And when we took those litmus tests where they behave differently and asked ARM designers, how do you explain that? And then they describe a thread subsystem, the execution unit, that behave pretty much similar to how the power does, out-of-order execution, speculation, in a very similar way, but a drastically different storage subsystem. In the way ARM designers talk about their storage subsystem is some kind of a topology of buffers where memory events flow in those buffers all the way to memory. In addition, the ARM architecture includes different kinds of memory accesses that don't exist in power and to be targets for the C11 sequential consistency computation, sequential inconsistency memory accesses. Along the years, we published quite a few papers about that topic. We started with the first model for ARM, and then we extended it with mixed size accesses, and then we simplified it, and then we added RISC-V support, and we're now starting to touch more system level things, which Christopher will talk later about. So we want to write a new memory model. We wanted back then to write a new memory model for ARM. How are we going to validate this new model? As you recall from the previous slide, the reference manual is incomplete. And we're going to have to do it using extensive testing, comparing the model to the hardware. And we're going to have to discuss it with ARM designers. If we're going to discuss it with ARM designers, it better be comprehensible for them. They usually use terms of abstract machines. So we went with an operation style, which is an abstract machine, inspired very much by the way they talk about their architecture. And here is how the outline of the flowing model of ARM. It's an application level instruction. It's restricted to application level instructions. Extensions, we added extensions later on. It can handle mixed size memory accesses. It has a thread subsystem based on the SAIL model. It can execute instructions out of order, starting by fetching instructions and then speculating as needed if it has bunches. And then, as you can see here, instruction I1 is being executed before the predecessor I0 has been executed. And now I decide to execute I0. Both of those generated memory events that appear in thread 0 inside the storage subsystem topology. Those memory events can flow down until they reach memory. This model and this architecture, the ARM, is at that point of time is non-multi-copy atomic. It means that when thread 0 value to X, thread 1 can observe the new value, while thread 2 is not observing it yet. And I don't have enough time to run through the whole example, so I'll just skip it. Turns out that non-multi-copy atomicity has the ARM memory model was back then. We're talking about 2016. It is relatively simple for regular memory accesses. It's getting a little bit more complicated when you throw into the mix the least acquire. Those are the targets for the C11 sequential consistent memory accesses. It's surprisingly complicated when you mix regular and the least acquires, and it's even more complicated when you add exclusive to it. So do we really need non-multi-copy atomicity? We've never seen any ARM v8 implementation that is actually I've seen a power machine that exhibit non-multi-copy atomic behavior, but we've never seen an ARM machine exhibiting it. And turns out non-multi-copy atomicity is not considered necessary by ARM for efficient implementations. They believe they can implement very efficient microarchitectures without using non-multi-copy atomicity. And the complexity of the model is horrible and no one can understand it or reason about it. So 2017, ARM decides to simplify the architecture's memory model. No more non-multi-copy atomic behavior. We developed, together with them, a new model called the flat model, which Christopher will show in a minute. Will Dickon from ARM, now Google, in collaboration with us, has developed an axiomatic memory model, which we've proved equivalent to the flat model, and the axiomatic the ARM reference map. For last, we also participated in the LISP-5 memory model task group, chaired by Daniel Lustig. And as a result, the LISP-5 memory model is very similar to the simplified ARM memory model. And the LISP-5 reference manual includes two axiomatic models and our operational model. All the tests that we used for developing the LISP-5 memory model are available in GitHub. And I'll turn over to Christopher now.
Okay, thank you. We could have a quick pause here for questions, but at the moment I see no questions. If anyone wants to type very fast while Christopher is changing over.
Yeah, Shaket, do you mind unsharing your screen? Thank you. I ask a question. I kind of loaded a question. So Shaket, you said that it's too complicated to make devices that are sequentially consistent, and yet the company that makes some of the most consistent machines are Intel, who have also some of the most complicated microarchitectures. So what's going on there?
I think I'm not an expert into implementations, but I think they pay some price for it in power and in the size of silicon and stuff like that. I think it's too difficult to, yeah, I guess they do some analysis and optimizations as needed, but they pay some price for it.
So I can also add something there. So a factor that ARM have mentioned in the past is that the validation cost of having a stronger model would bite them. It's just more quite twisty hardware that you would then have a significant challenge to validate the correctness of. With the relevant metrics are also different, right? So you pay a power cost for undoing these things, which for ARM may be more significant than for Intel. That's just speculation on my part.
I mean, if I could add, I suspect that's speculation. Do we actually really know?
Sorry, what do you mean?
Well, it's not clear that given that all the microarchitecture work that's being done on very strong memory models, it now doesn't appear to be quite as costly as people first thought.
So I've spoken with many industry hardware architects about what they think the cost or benefit of being relaxed is. And it's very difficult to assess because the mature industry architectures have each been developed and the microarchitectural optimizations have each been made in the context of the initial architectural choice. So for example, if you ask the IBM power folk how much they think they benefit, it's really not possible for them to say. I mean, they have some gut feeling, but they've made so many other decisions in the context of that initial choice that it's not obvious how it would work out if you made them the other way. It's not clear that it's an answerable question, really.
As an anecdote, we do see devices that are sequentially consistent, ARM and RISC-V.
Some, yeah. But then if you look at high performance, very multi-core power servers, we see that they are sometimes very not sequentially consistent.
Indeed.
Yeah. Okay, let us move on to part 2, Christopher.
Okay, so Shaq had already told us about our work for the non-multi-copy atomic ARM architecture. After this architecture revision, ARM v8 is now multi-copy atomic, and so is the newer RISC-V architecture. And so in this bit of the talk, we'll look at their semantics, the equivalent models in 3 different styles we've produced together with our colleagues for these architectures, executable tools around them, and more recent extensions to these semantics. Okay, we'll start by briefly returning to this flowing model picture. So if you remember, flowing consists of these 2 subsystems, thread and storage subsystem, where the storage subsystem is in charge of the propagation of read, write, and barrier events between the threads. And now, multi-copy atomicity means that when the write is propagated from one thread to another, it has to, at that point, be propagated to all other threads at the same time. And we can achieve that in the flowing model by instantiating it with a flat topology, like you see here. But as it turns out, we can do better and simply replace the storage subsystem by a flat memory, which is just a mapping from addresses to values, basically. And this is our model for the multi-copy atomic ARM and RISC-V architectures. What you're left with then is this interestingly relaxed thread subsystem that's running the sale semantics that Alistair talked about for the ISA behavior. In the case of ARM v8, that's a sale model for large parts of the user mode architecture. In the case of RISC-V, the full official RISC-V sale model. Now to take a look at this in more detail, let's look at this example, which is an example of a message passing program implemented in ARM assembly, but feel free to just look at the comments on the side, the pseudocode. So we've got 2 threads, a producer thread and a consumer thread. The producer thread produces some data, here the value 5, and writes it to X. Can you see my mouse, by the way? I shouldn't ask that live, I guess. So yeah, I'll highlight this. The producer writes 5 to X and then sets the flag to let the consumer know that the data is now available. And because we know ARM has that relaxed semantics, we put in a full barrier in between the 2 stores to keep them in order. So now the consumer reads the flag, and if it sees the flag set to a non-zero value, it goes and reads the data, and otherwise does nothing. So for this code to work correctly, we'd like it to be the case that the consumer can never see the out-of-date value for the data after reading the flag. So is this code correct? One way of telling it would be to run it inside our RMEM tool, which is this tool for running executable operational models, all of the ones you'll see in this talk. And you can run code interactively, exhaustively, pseudo-randomly. And this is code in 2 formats, either as litmus tests or as Linux ELF binaries. And now I clicked on this link, which I hope everyone can see. This is in the browser loading up RMEM with that test preloaded. On the left, you can see this console that you can ignore now. And one thing I can do now here for these smaller kinds of tests is tell it to do an exhaustive search of all the architecturally allowed outcomes. And what this does is it spits out, I'll zoom in, a list of possible final states the architecture allows. This is, for example, this state here that is the one where the consumer thread read the data, correctly read the value 5 for the data. But indeed, it also contains the outcome here, where after reading the flag, it sees the stale value 0, the initial value for the data. And now I could click on this link to replay that trace and see how that works. But here I'll just do that manually for a bit. Zoom into this test. So what this is a view of the operational model state. In the initial state, we have an empty memory over here and empty instruction trees for each of the threads. And what I can start doing now is fetching instructions. If I do that on the consumer thread, thread 1, it gives me that first load instruction, which is a load of the flag location. And I could start executing that load now by doing its first action, which is a register read, or continue fetching subsequent instructions, which gives me that conditional branch, which at this point, because we haven't read yet, is completely undetermined. So both sides of the branch are possible behaviors at this point, and I can explore both sides. So if I now make a guess like a branch predictor might in the CPU and say, probably the branch won't get taken, and fetch the immediate successor instruction, that gets me that second load of the data, which I think I accidentally clicked one step already. I can do that register read that it just had, and now initiate that memory load, which announces its address to the concurrency model. And at that point, I can start satisfying it from memory. And because at this point, we haven't done any writes to memory yet, this would read the value 0 from memory. And if I do this now, we've already got the interesting part of that execution to make this bad relaxed behavior happen, where we've just done this, what will later be the stale value for the data. Okay, so I'll briefly return to the slides. So that tells us that code is broken. What can we do to fix it? One way of fixing it would be to upgrade that first load of the flag to be an acquire load, which gives it special ordering properties and means that the second load has to execute after it. It can only be satisfied once that first load is satisfied, and prevents this bad execution. So this code is now fine. Okay, so that tells us a bit about that operational model. If you remember from Shaket's part of the talk, in parallel to this, in the case of ARMv8, and co-designed with this flat model was the official ARMv8 axiomatic model, and this was done principally by Will Deacon. In the case of RISC-V, the memory model task group that we also joined later decided on a multi-copy atomic axiomatic model very similar to that, and this was done also especially by its chair, Daniel Lustig. So what is an axiomatic model? You can think of it as working in 2 steps. If you have a given input program, the first step is to enumerate the possible candidate executions of that program. And that means enumerating all the possible concrete hypothetical executions of that program if we assume the concurrency behavior is unconstrained. And for the sake of the axiomatic model, these executions are abstracted as in terms of memory events, read, write, and bury events, and relations over them. So to make this more concrete, if we return to the message passing program with that acquire load, what we get is a bunch of candidate executions, one of which is the one where the consumer correctly reads the value 5 for the data, but also the one where it reads the stale value and others. And these candidate executions now contain 2 write events here, one for each of the stores on the producer side. They're ordered by the relation called program order, which corresponds to the control flow order in the originating program, and separated here by this bury event. On the consumer side, we have 2 reads, one for each of the loads of the program, and separated by a control edge originating from the conditional branch on the consumer side. The reads from relation records which of the writes the reads read from, and in the case of this stale read here, it's the initial write. Okay, so we get a bunch of candidate executions. The second step is now to check whether the axioms of the specific model we're looking at hold for it and rule out the ones where they don't. And that looks like this. In the ARM case, the RISC-V case is basically the same with minor changes. This model now, so there's two parts. In the first part, until here, it defines a whole bunch of derived auxiliary relations that specify some ordering requirements about the memory events of the candidate execution. And at the bottom here, you see the bottom three lines are the three axioms that each candidate execution has to satisfy in order to be an architecturally valid execution. And here I'll only have time to talk about that second main axiom called external. So what are these ordering facts that these relations specify? If you start looking at the top, for example, it says RFE, that means read from external, which is a relation about reads from between two different threads. So if you have a write and a read that are related that way, it means the read has to effectively happen after the write. Similarly, there's some ordering requirements originating from thread internal dependencies and explicit ordering coming from barriers and so-called atomic instructions. And now the external axiom requires that the union of all these order-inducing relations has to be irreflexive or acyclic because it's transitively closed. So if we look at that example again, this graph you see here is the same graph as before, just now with a from reads edge, the derived from reads relation added. And you can see already that the graph forms a cycle. And if we step through, we'll find that each of these edges here is included in the ordered before relation. On the producer side, we've got this edge connecting the two writes because of the barrier, says the barrier ordered before relation here, reads from edges between two threads, induce order by the observed by relation, and so does the from reads edge here. In this case, the barrier ordered before relation also tells us that read acquire induces order with respect to any subsequent program order later reads or writes, which closes this cycle. And means, because we've now got a cycle in ordered before, that this is an architecturally forbidden execution. But if we return to that previous example, the one where we have the weaker, the standard relaxed read for the consumer thread, then this execution, even though you see a cycle again, this is an allowed execution because this is not a cycle that the axiomatic model considers to be a bad one, because now that this read is no longer an acquire read, the control dependency between these two alone is not strong enough to keep them ordered, because reads are allowed to be executed speculatively, as we saw in the example run in flat. Okay, so that's roughly how that axiomatic model works. What can you do with it? One thing you can do with it is you can execute it with different tools. And the existing tool here is the HERT tool by Alglav, Maranger, and Tauchnik. But this comes with a smaller and only ad hoc instruction semantics. And so we also have this newer tool called Ale Axiomatic. Now, oops, Alistair was talking just before me, so I'll just briefly mention this. Ale Axiomatic by Alistair Armstrong is a tool for running these axiomatic models integrated with SAIL ISA models. It works by symbolic execution, and there's a RISC-V and an ARM variant at the moment. And in particular, the ARM variant has this bigger ISA model. That's the full ARMv8 ISA model as derived from the vendor internal specification language. And if you want to try it out, in the background you can see a screenshot. The abstract has a link to that. Okay, so two different models for the same architecture. How do these two models relate? Well, for the case of the ARMv8 user mode architecture, and under the assumption of non-mixed size programs, we have a detailed hand proof of their equivalence. So this is a proof relating these two models of very different shape. And the way it works is that it establishes a correspondence between transitions and events. And then according to that trend, so it then uses that correspondence for both directions of the proofs. So if you assume you've got an execution allowed by the flat model and want to show it's allowed by the axiomatic model, you can view the operational model trace as an event relation according to that correspondence and use it to justify the acyclicity of the ordered before relation. And the other way around, if you've got an axiomatic model allowed execution and therefore an acyclic ordered before relation, that gives you clues about how to construct a witnessing flat model trace witnessing the same execution. Okay, so flat operational and axiomatic, why even have two different models for the same thing? Well, they have different advantages and disadvantages. The flat operational model is nice in that it incrementally computes the traces of the allowed executions. And it's also good because it has a closer relation to the hardware, which has been crucial for establishing confidence in the model by discussing the model with the ARM architects, especially in the case of flowing. As a result of this closeness to hardware, however, it's also quite complex. The axiomatic model, on the other hand, is nicely abstract and concise, but does not have this incremental property. It's specified in terms of global properties of completed executions. Now, all good things come in threes, and so we've built another model for this, which tries to, for the sake of, for a focus on software and software correctness, tries to combine the abstractness of the axiomatic model with the incremental nature of the flat operational model into a new model called Promising ARM RISC-V, and it's called like that because it's inspired by the promising semantics for C11 concurrency, and it applies the ideas from that semantics to architectural models. It explicitly gives up on this nice close relation to hardware that flat has, but what you get out then is an operational model that's simpler because it does not need branch speculation. Each instruction executes in a single step only as opposed to multiple. All instructions execute in program order with the exception of the promise step. Now we don't have mixed size support working yet, but would like to fix that. And we've got a COC proof of equivalence with the ARM v8 and ARM v8 and RISC-V axiomatic model. And one thing we've done with this is implement some optimizations that make it fast enough for checking some small but interesting concurrent data structure examples, sort of in a model checking kind of a way. And you can read more about that in the paper. So now to shift focus a bit, all the models, these three models you've seen so far, they all make a bunch of assumptions. They're targeting the user mode architecture, and they assume a fixed program memory that has no exceptions and no virtual memory. And these assumptions hold for a large and interesting class of programs, but not if, for example, you're looking at operating system code. And so what we're working on now is extending these models to cover more of these systems aspects. What we've done here so far, and we here is Ben Simner et al., is look at the semantics of instruction fetches and self-modifying code in a concurrent setting. So one thing you can do there is look at small programs like the one you see here, which is another kind of a message passing program, except that the producer thread is now producing code instead of data. That thread 1, the consumer thread, after getting past the flag, is expecting to fetch and execute. Sorry. And one thing one might ask now is whether, after seeing the up-to-date value for the flag, the consumer thread is allowed to fetch and execute some NOP instruction that might have been in memory before this add instruction here, or whether it has to execute the up-to-date instruction memory. So to answer questions like this, we've extended the flat and the ARM axiomatic models, both in the case of ARM. And what you get then is a picture a bit like this on the left, where you've got a couple of extra components added to flat. There's something called a fetch queue as part of the thread semantics. We have models for abstract instruction and data caches, in which the instruction fetches and writes can float around. And on the axiomatic model side of things, we add some new kinds of events and relations to the official ARMv8 axiomatic model, and relations that capture their interaction with the rest of the model. Both of them are executable. The operational model side of things using the extended flat model inside of RMEM, the axiomatic model one using the Euler tool that you saw earlier. And you can read more about that in the ESOP paper. Okay, and to briefly conclude, because I think I'm running over time, there's a couple of outcomes of this line of work. The first point is these architectural changes. So partly as a result of our work, ARM revised their concurrency architecture. They shifted to a multi-copy atomic model, and their architecture documentation now has an official formal axiomatic concurrency model. RISC-V later on also adopted a multi-copy atomic semantics, and along with two axiomatic models contains our flat RISC-V model as part of the documentation. Well, the other outcome is that we've produced these formal models that we'd like people to try out and use and build on. And these are these executable operational and axiomatic models integrating the SAIL isosemantics. We've got some equivalence proofs for the user mode architecture, and we've built extensions on them to cover more systems aspects. And all of these things are available online if you check this GitHub page, and currently or very soon also as OPAM packages. Thank you.
Okay, thank you. We have time for some questions, if we have some questions. Nothing so far in the Slack, so we'll give people a few moments. Maybe people have already exceeded their threshold for electronic interaction, which bodes poorly for the rest of PLDI, but hey. So Mario Carnero asks, do you have any thoughts on why hardware manufacturers don't go to a more relaxed memory model?
Because it's hard to get it right? No.
Your audio isn't very good, Shaked.
I said because it's hard to get it right. And maybe because the architectures are not, until recently, weren't well enough specified to be sure that you're in the right boundaries. But that's just guessing.
So I think that's a part of it, but there's also a big part, which is that even though the architectures have not been terribly well defined, there is an implicit definition out there, which is very hard to change, which is the assumptions that the code implicit of Linux and Windows and what have you implicitly makes. And if you suddenly make your hardware architecture more relaxed, you can expose those assumptions in ways that you don't like. So I think there's quite a lot of commercial pressure for the existing architectures to not make them more relaxed. It also, interestingly, kind of goes the other way. So when ARM strengthened their model to forbid non-multi-copy atomic behavior, as Shaked and Christopher described, they could only do that really because there were essentially no hardware implementations out there that had the more relaxed behavior, and hence no implementations for which new software would fail on existing in the field implementations.
So another aspect might be that if you make the architecture too relaxed, and any kind of reasonable programs people might write will require barriers and special annotations or dependencies everywhere, performance might have the opposite effect.
Yeah, it's hard to predict.
You might make things slower than you'd want it to.
So Mario glosses the question, for example, something based on message passing. So maybe I'll answer that. So in the implementations of these, there is a lot of message passing. This shared memory abstraction is just one that happens to be rather convenient for software. So you can imagine another world in which the main hardware abstraction exposed to software is message passing based, but then it might be that for any software that really does have to access a lot of data and do a lot of concurrent computation on it, it might be that the first thing that software would do would be to implement a shared memory abstraction above the message passing. It's hard to predict, and it would be a big shift.
I think
sorry, go ahead.
Yeah, so I think from a programming language perspective, it is exactly as you say. There are some things that might like it, but it will be a huge shift. And I can see a real gap here that, as you say, the hardware implementation often involves quite a lot of passing messages around in order to have, in some sense, fake a more sequential model. And there are certainly programming languages that would like more or are much happier than perhaps they used to be with loosely coupled systems or non-shared memory systems and message passing. But at the moment, it all has to go through an interface, either a lower level language, an intermediate representation, or an assembler, which has a shared memory model. And if we could bridge that, I think it would be great, but there would be a lot of layers in the middle that had to change. And it might be that the message passing memory model didn't match up that well with a programming language level message passing. So it might be a win, but you'd have to educate all the layers in the middle about message passing and get them to match up.
Yeah.
One day maybe.
Elliot Moss remarks, this is another question, I would ask more questions about more details, but I feel I need to see and read the paper first, smiley face. There are a number of papers that we hope it will be a pleasure for you to read. William Wang asks, what about the other way? But I don't understand the question. Which other way? Oh, why hardware manufacturers don't go to a stronger memory model? Christopher, Shaked?
Well, I guess what we said about TSO might be true there, that I think in the past, also in the context of RISC-V, it's been said that Intel has a lot of manpower and money to put behind the development of machines that are fast and efficient and whatever, and present this stronger model, but anyone who's not Intel might not be able to get the performance to a good enough level while having that strong semantics, or there's power efficiency problems or validation problems also. Yeah. But there's only one side of the picture probably.
Thomas Sewell comments that he suspects that currently lots of computations that work well in a very loose memory environment, so I guess a very relaxed environment. It's not clear if he means very relaxed or very message passing, but will be run on GPUs, FPGAs, or distributed setups, which is also surely true. Right? All of this work so far is talking only about classical CPU computation, really. Well, no, that's not true. So GPU models have been studied, especially inside NVIDIA. There's a bunch of work on that, and they are not that different to the models that you see here, the relaxed models of GPUs. Okay, if we have no more questions, then we have time off and we can talk among ourselves, or as somebody suggests, eat popcorn until the next hour boundary, when we shall shift to sophisticated high-level languages around the level of C. See you then. Oh, Benjamin comments, we have created a REMS DeepSpec room in the Clouder social space, which you can get to by doing /video REMS-DeepSpec. I wonder if that.
Where do you do all these / things? Just in the message window?
It's / and it's in Slack.
Yeah,
Sorry.
In the Slack message window, where I would type a message.
Yes.
Yeah, so / if you do /video and then send that as a message, in fact, it doesn't appear on everybody else's chat. It's you talking to some bot in there, and it will then talk back to you.
Thanks.
Then you have to click a bazillion clickers. Oh, and then you have another shared video thing. Hello, Benjamin. Hello, Beta.
Yes, we have another shared video thing. Isn't that great?
You don't want that.
Should we wait another 2 minutes and then start? All right, thank you all for coming back. This is now the session on the specification of the C language, the specification and verification. And the first talk is by Kaiwan Memarian from the REMS project. Take it away, Kaiwan.
Can you all hear me?
Yes.
Okay. Yeah. So I'm going to talk to you about the Cerberus project, which is from Cambridge, where we've been working for the past few years in building an executable semantics for the C programming language. And in particular, we've been working on studying the memory model as described by ISO, but also as it is used in practice. So the C language is defined as an ISO standard, which is a contract between compiler writers, people implementing the language, and their users, which are system programmers. And this standard is written and maintained by a group called WG14, who set themselves the goal to design a clear, consistent, and unambiguous standard for the C language. And the need for this standard arose from the time where C started being implemented in very different architectures and very different operating system, where implementation defined choices made the behavior of program different across architecture, and a common language was necessary. So when you take the C standard, it's a big document, and basically, three kinds of people are going to read that document. On one side, you will have system programmers, who are the people actually using the language, who will read the document and make some set of interpretation, either based on their reading of the standard or also based on the actual need they have for the language. On another side, you have a compiler implementer who will also have their own interpretation of the language. And more recently, people writing static analysis tool and people doing a formal study of the language. Unfortunately, it's not clear how these different readings relate to one another. And in fact, there are observable differences between their interpretation, but also between their needs. So this is mostly coming from the fact that the specification is a huge document written in prose. Despite that, it does succeed in clearly defining a big chunk of the language, namely the syntax and the type system, but also since C11, the concurrency memory model, and a big chunk of the dynamics of expressions and statements if you ignore the memory model and the semantics of pointers. Regardless, the fact that this is prose and not an executable model makes it very hard for someone to take a small C program and easily find out what are all the allowed behavior of the program, whether there are implementation-defined choices which will impact the observable behavior of the program on one architecture or another, whether there are undefined behaviors. There are also really strong disagreement between what the standard describes and how the language is used in practice. And this is mostly with regard to the memory model. In real life, this disagreement between the standards and practice, but also between the different readings of the standard, have real-world consequences. Just looking back a few years, for example, you had CVE in the Linux kernel, which could simply be explained by the fact that something was undefined according to the standard, and compilers were exploiting that fact to remove some code which was necessary to prevent an exploitable attack to occur. So the compiler was correct to remove some piece of code, but the system programmer who had read the standard had not caught that undefined behavior. So the goal of the Cerberus project is to design an executable and precise semantic for a large fragment of C that one can use as a test oracle. We try to stick really closely to the ISO standards, but when the standard is unclear or diverge from de facto use, we try to incorporate de facto use and extend and go beyond what the ISO standard describes. We have from the beginning support for concurrency and parametricity over implementation defined behaviors, and we've been using that artifact as the basis of ongoing discussion with the WG14 committee to try to change parts of the ISO standard where the memory model is not precise enough. To give you a timeline of how this project arose, in previous work in our team, mostly Marc Batty et al., we were working on mathematizing and repairing the C++11 concurrency model, which was later also added to C11. And at the time, the concurrency model was connected to a very restricted toy thread local semantics, and we wanted to extend that to a more realistic model of the language. And when we started doing that, by just trying to formalize the ISO standards, most of the language could easily be formalized, but we came up with a few areas of unclarity: the semantics of pointers and the semantics of unspecified value. So since it wasn't clear what the semantics should be, and since we're not really system programmers, the first thing we did was to start asking questions to the practitioners and people writing the compilers to know what their opinion on the semantics of these corner cases were. So in 2015, we made a survey that we passed around to a few hundred people. And the first thing we noticed was that there were conflicting answers, and we couldn't synthesize from the results coherent semantics and a coherent memory model in particular. So we started attending the WG14 meetings to try to clarify the C object memory model, and we've been doing so for the past few years. And at the time, there was already the problem was already known from the WG14. There was a document called DR260 where some notion of provenance for pointers was hinted at, but never fully defined. And in the work that that I'm presenting here, we are making a formal definition for what that provenance hinted at by DR260 is. There is, of course, been lots of related work on the formal study of the C language, but also studying the memory model and extending it. What the main distinction of this work is that we try to go beyond what the ISO standard defines and try to observe the de facto use of the language and synthesize a model for it. So in the rest of the talk, I'm first going to talk about the Cerberus C semantic, just to give you an idea of how it is structured. And this is mostly going to talk about the part where the C standard is not controversial. Then I will move on to provenance-based memory model, which is the area that we're trying to clarify in the ISO standards. Okay, so just to remind ourselves, what are the main issues with making a model for the C language? The biggest issue is that in the syntax of C expressions and statement, there is a lot of hidden complexity. And a single C construct will do many things at the same time. So for example, in expressions, in arithmetic expressions or others, there is a very loose and intricate ordering. If you consider the expression on the left, which shouldn't appear to be doing very complicated things. If you were to write a graph where every node is a memory access, load or store, and every edge indicates that an access must appear before another one, which is the SB relation in the parlance of the C11, C++11 concurrency model, you would get the graph which is on the right, which is surprisingly complicated. You also have implicit boundary of object lifetime, in particular tied to the definition of blocks and local variable within blocks, which means that it's quite easy to construct a pointer to an object that will have been deallocated before the pointer is used. There are also implicit type conversions pretty much everywhere as a result of the fact that you have various integer types with different sizes. And when you mix them together, you don't need to do explicit conversions. Instead, there are some complicated rules for attempting to do the less surprising thing for the programmer. And for example, in the example I'm showing you here, we're doing some arithmetic that goes outside of the range of the assigned car type. But because the final result is within that boundary, the final result is not destroyed, which is good. But then you have corner cases like comparing something that you would expect to return true, but because you're comparing a signed and an unsigned value gives you a counterintuitive result. And this gets even more interesting when you mix these implicit conversions with the fact that some things like, for example, the sign of car is implementation defined. If you were to run this program that appears to be constructing the same value in two different types and then you compare it, if you run this on an x86 platform, for example, it would return false, whereas it would return true on an ARM64 architecture. Okay, so for all these aspects of the C semantics, the standard is really clear. And it is fairly simple to formalize it. The main issue is that if you were to directly give an operational semantics, for example, directly on the AST of the C language, you end up with a very bloated operational semantic because too many things are happening at the same time. And this is going against one of the goals of the Cerberus project, which is to have some sort of model, some sort of definition of the language, which is more rigorous than the prose, that can still be read by people who know the C standards, which are not semanticists or PL researchers. So instead, we decided to define the language by elaboration, which means that instead of directly defining the dynamics at the level of C, we designed a language called Core, which is the simplest language we could come up with for which is explicit enough in a nice way to express the dynamics of a C program. Basically, it's the language you need to translate the current English prose of the C standard into something which is machine checkable. So the basic structure of the semantics is a bit like a compiler, but instead of doing progressive refinement of the semantics of your program, we are completely preserving it, and we don't bother ourselves with being performant, but instead we want clarity. So the core language is really simple and also amenable to be given traditional dynamics in a traditional operational semantic style. It is a first-order functional language with strong types. It has a type-directed distinction between expression that cannot touch the memory and ones which do, and therefore for which sequencing matters. And it factors out the memory model so that you can elaborate a C program into a core program without having made any decision on what the semantics of pointer is. So just to give you a taste of what this looks like, on the left, you have an excerpt of the C standards, which describes the typing, syntax, and dynamics of the bitewise shift operators. And you have some text talking about its typing rule, basically. And the thing I'm showing you on the right is one clause of the function taking a C AST and turning it into a small core program. And this is just the clause for the particular AST node of the left shift operator. So as you can see, this gets turned into a rather large program, but everything becomes explicit. So for example, the implicit type conversion I mentioned earlier are simply modeled by calling a pure function that takes a C type and an integer value and is going to perform some arithmetic. And this function itself is written in core in a rather straightforward way. This operation has some undefined behaviors. For example, if the right operand is less than 0, and this is explicitly modeled by having an undefined constructor in the expression language, which just signals that the error happens. So using that small core language, we can really make all these implicit behaviors I mentioned earlier just visible in the syntax. So for example, if you consider this small program on the right that only has a global variable, a pointer as a local, and then try to sum loading from the global variable and dereferencing the pointer, we make explicit allocation events, loading and storing, checking whether a pointer is valid, all the events that involve talking to the memory explicit. We then make also explicit the complicated sequencing order between these memory access, and in particular the fact that the access of inside the operands of the cluster on sequence is expressed by some operator forming a small calculus for sequencing. We make undefined behavior explicit, implicit type conversions, the fact that we might be reading an unspecified value, and so on. Just to give you a very quick idea of what the language looks like, it's really just the core language. It really just started as a simple functional language. So we had like variables, the let and if and arithmetic, and we just added the construct that we needed. So an explicit undefined behavior constructs, operators for doing pointer arithmetic and constructing struct and union values and so on. Then on top of that, we have the effectful language, which starts from the pure language, but also adds memory interactions in the form of either actions or like equality operator between pointers and things like that, which are then combined within a sequencing calculus here shown in green for saying that actions are sequenced or not sequenced. And then because, of course, C has goto, we have basically a generic, a bit more complicated notion of goto, where we desugar pretty much every control flow operator into. Using this elaboration pipeline, we've made a tool which satisfies our goal of obtaining an executable oracle for C. It allows you to run reasonably sized programs in a random, exhaustive, or interactive way. And you can instantiate it with the particular implementation, so the size of integer types that of your compiler and platform. And we have a web interface that makes it easy to access, and in particular, you can visualize the memory states. So this is what it looks like. Because we also wrote our own front end where we try to be preserve. Well, we annotate the generated AST with basically the sentences of the system that requires us to generate the AST in the way we did. We can track all of this information throughout the pipeline. So it makes it easy, for example, to just relate this big blob of core program that are quite big compared to the original C program and get justification. And the user interface allows you to see which part of the standards mention that. Using the exhaustive mode, you can also have a symbolic memory allocator, which allows you to explore the range of possibilities of how objects may be placed with respect to one another. And for example, this little program shows you that you can sort of establish the fact that the less than operator between pointer is transitive. And this is what the representation of memory model look like. You get boxes, and you can get graphical representation of which pointer object point to, and this is useful in the next part of the talk, where I'm going to show you how pointers with provenance work. Okay, another tool that was built later on is a bounded model checker for the C11 relaxed concurrency. And this was done without having to redo any work on the C semantics at all. This was just done by mapping the generated core language into an SMT problem, which shows the advantage of having an elaborative approach, because we can just reuse without touching it at all the work that has been done to precisely specify all the complicated aspect of the expression, the C expression language, and really just focus on building an analysis tool. Okay. Another advantage of having an executable model that can scale to a reasonably large program is that we can, since we can't formally prove that the model is correct because we're trying to make the model, we can instead do differential testing to see if it at least matches what a compiler do. And for example, since the early ages of the Cerberus, we've been validating it by running it on randomly generated programs using the CSmith tool and comparing the results of compilers without using the optimization level. And since compiler like mostly correct unless you make big programs that might trigger optimization, it is a reasonable way of establishing some sort of confidence on the model. And we've then used various test suites that exist already for compilers and just random handwritten tests. So this concludes the part about the Cerberus model, and now we're going to move on to the notion of provenance for pointer, which is one of these ambiguous parts of the current ISO standard that we're trying to clarify. So if you think about a memory model for C, you can think of a spectrum with two extremes. On one hand, you could think of pointers as being fully abstract, and memory objects are islands completely isolated from one another. And then you have some restriction on what you can do with pointers, which is somehow enforced by the language. On the other hand, you can take a very concrete view where the memory is just a finite map of numeric address into bytes. And this sort of matches the underlying implementation on current hardware. And you can interchangeably use pointers and integers. In the original KNRC language, before the ISO standard came up, it was mostly concrete. But if you look at the ISO standard, there is a fair amount of abstraction, and you're not really allowed to do everything you want with pointers. However, the way the language is used is more abstract than what ISO describes, which is itself more abstract than the fully abstract view of the memory model, because there are optimization that we observe compiler doing, which cannot be explained by fully concrete memory model. At the same time, you don't have a complete separation between the integer word and the pointer word. It's quite common for low-level programs to cast a pointer to an integer and then manipulate its representation, like for putting like metadata, for example, inside pointers. Okay, so the most interesting part for us is the fact that pointers are quite abstract. And this is hinted at, as I said earlier, by some response by the WG14 committee to a question called the R260, where they say that implementation are allowed to track the origin of bit patterns of pointers, and that they are allowed to treat two pointers which have the exact same representation as being pointing to different objects. And we do observe this in practice because compilers have been using alias analysis-based optimization for quite some time now, and they do implicitly rely on that notion of provenance of bit pattern, and it's quite easy to observe it in practice. So this is what we're going to look at now. So consider this very artificial program that no one would actually write in practice, but which has become a classic in the literature to show that alias analysis does break the concrete view of the memory. So you have two global objects, y and x, two integers, and we are going to build two pointers, a first pointer p, which is going to take the address of x, and then go one past that object. And we're going to be interested in executions where we know that x and y are allocated one after the other. So graphically, this is what we're going to. We're going to get a pointer that morally points to y, even so we've constructed it from x. And then we have a pointer q, which is just constructed by taking the address of y, so it's clearly a valid pointer for y. In the if then else, we're going to check that these two pointers indeed have the same memory representation. And if they do, we will try to access the object y through the pointer p by doing a store. So in a concrete view of the memory, this should work. This should write 11 in the object y. And if we were to load y and dereference q, we should see that value 11. Unfortunately, if you run that on GCC or Clang with some optimization level sets, what you will see instead is that the referencing from P, which is the pointer we've just used to do the store, will observe the value 11, but the two other ways of accessing Y do not. So how can we explain with a very simple semantic tool this behavior? So what we want to do basically is to make this program undefined behavior because we want to leave freedom for compilers to either do the optimization or not. So in the C abstract machine, what we're going to do is we're going to make pointer values a bit more complicated. And this is only at the level of the C abstract machine. This is no requirement on how things need to actually be implemented. So now pointer values are going to be a pair of an abstract provenance, which can either be an empty provenance, that means that the pointer does not refer to, is not a valid pointer to any object, or is a concrete provenance to some unique ID referring to a particular memory object. And then the second component of the pointer is just the numeric address like we have in the concrete view of the memory. At every allocation time, the abstract machine is going to pick a fresh ID for the newly allocated object, and the pointer you get out of the allocation will have the provenance associated to that ID. Then we need to update all the arithmetic operators of a pointer so that they somehow preserve the provenance. And then now, crucially, in the semantics of doing memory access, what we're going to do is that when a pointer is being used, we're going to look into a go state, which from an allocation ID can give us a footprint of associated to a memory object, and we will check whether the numeric component of the pointer is within that footprint. If it is not, then the memory access is undefined behavior. So going back to the previous example and now using the web interface to visualize what happens in this model, we have the allocation of the two global objects and their initialization. We have and by allocating these two objects, the memory model generated two fresh identifier, 0 for y and 1 for x. When we create the pointer p, we take the address of x, which is a pointer that has the allocation ID associated to x, so 1, and then we do the arithmetic. So the pointer value p will have the allocation, the provenance associated to the object x, despite the fact that after having done the +1 operation, the address now points to morally the beginning of the object y. So the two pointers p and q have the same representation but different provenances, and only q is allowed as a pointer for dereferencing. So the line 10 in our program has now undefined behavior, and the optimization with observed GCC perform is now sound. So this is a very simple mechanism, but now the challenge is to make sure it scales to all the different ways one is allowed to build pointers in C, and there are many of them. We can freely cast from pointer to integer and go back, and this is the extent to which the standard allows programmer to perform this cast. But in practice, people will also do some arithmetic in between, just making sure they reverse them before casting it back. You may want to implement memory copy operations, manipulate the representation of pointers, do reinterpretation of bytes using union typing, and so on. The model also needs to be useful. It needs to support all the common idiom that we find in low-level programming. So just a concrete example, in an implementation where you know that signed int object have some alignment constraint, you know that some of the bits in any pointer to an int object will always be 0. So you can temporarily store metadata in these bits, and as long as you remove them before actually using the pointer, everything should work, and this is common practice. Another thing that is crucially needed for the model to be useful is for all these optimizations that we're trying to justify, you're trying to make them sound with respect to that model, we need to support them. So there are loads of assumptions that compiler make about which pointer may alias or which pointer may be assumed to not alias with other pointers. We need to preserve all of these. And this is how, by looking at on the case-by-case basis at whether these optimizations are supported, this is how we can establish some form of confidence in our model. So over the years, after attending many meetings of the WG14 committee and talking with various compiler implementers and practitioners, we came up with a model we call PNVI, which does satisfy all these constraints I just mentioned earlier, and we've established that by building over the years test suites of programs. And crucially, it does not need to track provenance on integers, which is good because integers remain integers. They don't behave like pointers, and all existing arithmetic algebra-based optimization on integer should still be sound with respect to that model. Instead, what we do is that when an integer is being cast to a pointer, we will have some machinery to look at the go state of the memory and try to retrieve a provenance based on the existing objects. And we have a few variants of this model, which put some varying restrictions on how much how much information can be retrieved from the go state. And in particular, there is a preferred variant by the WG14 committee and also the undefined behavior subgroup of the C++ committee, which we call a PNVI UDI, where we only allow cast from integer to pointer to produce valid pointers for objects that in some way have been exposed, which means that, for example, for pointers, for object for which the address has been taken and explicitly cast to an integer. And this somehow mimics what alias analysis in compilers like GC and Clang actually do to compute these sets of potentially aliasing objects. And we also have some complicated machinery for dealing with round trip of one-pass pointers, where some ambiguity exists because you have an integer value, but you have morally two objects it could be seen as a pointer to. So this model has been tentatively approved by both WG14 and the undefined behavior subgroup of WG21, pending some investigation on the impact on implementation, in particular the performance impact. And you can find a formal presentation of this model and the other variants in the link at the bottom. So to conclude, we've been building an executable semantics for a substantial fragment of C as described by ISO, but also going beyond for some aspects which we found unclear. You can use it as a test oracle. It is parametric on implementation defined choices, doesn't make any upfront assumptions. And it's been used as the basis of ongoing discussion with the ISO committees to try to clarify the C object memory model. It has a web interface that you can use, and there is a link in the web page shown, whose URL is shown at the bottom of the slide. Thank you for your attention.
All right, thank you very much. And maybe not surprising, there are 5 or 6 questions on C immediately, mostly on connecting your tool and using it. So let me start with the first question by Andrew Appel. So from a core program, can you recover a syntactically and semantically correct C program, not necessarily the same one from which you obtained the core program? That is, can you pretty print core as C?
We don't have that facility right now, but so the types are really abstract because the type in core, I mean, the values over which a core program operates are the abstract notional value of the C standard. So it's not clear you would get something really nice. We have one intermediate language within our pipeline, which is the one coming after the type system, and in particular after implicit type conversion, which you can pre-imprint into something that would be parsed by a C compiler.
Okay. Then a question by Sasha Eliayun and refined by Andrew a little bit further. So is the source of the compiler to core available? Has core ever been used as an IR for static analysis? And the addition then, is the compiler not only available, but actually open source available?
Not yet, but we will make it open source in the next few months. For the question about whether core has been used for static analysis tool, within our group, we made some experimental abstract interpreter using core. This was mostly a toy thing, so it's not a full-fledged abstract interpreter, but it sort of works. We've also we have a symbolic mode that maps core into an SMT backend, and you can use it to sort of prove behaviors by asking SMT questions about it.
Okay, next question from Mario Canero. As a programmer who wants to write programs with a formal semantics, I have no interest in C as such, but want to be able to use a C-like language in its role as high-level assembler. Is core a reasonable choice of language for this use case? For example, writing core ASTs directly from within COC or another proof assistant? And in particular, then, is there a compiler for core programs?
So there is only an interpreter for core. We didn't really design core as we only designed it as a language so that we could express the text of the C standard. So it is definitely not pleasant as a language to write by hand. On the other hand, we don't have that infrastructure right now, but we ideally would want it to be usable as a specification language that you could map into core. But the idea has always been to start from C and then generate a larger core automatically from the C source. You could map another source language, but that would require writing another elaboration.
Okay, next question by Subha Sharma from IIT Delhi. I'm curious about Cerberus BMC's ability to analyze C11 concurrency. In particular, what fragments of C11 concurrency is currently supported?
So you can give it the model you want. In fact, by giving it I forgot the name of the algebraic language where you describe the axiomatic memory model. So we have the RC11 memory model and I think the canonical C11 memory model.
Okay, next pair of questions again by Andrew. Can you compare your provenance with a composite memory model that uses abstract block numbers to accomplish the same kind of thing? And especially in relation to the pointer integer casts as a POPL paper proposed 2 or 3 years ago did.
So it is observationally quite similar. The main difference is really just in the style, which makes it easier for us to convince the ISO committee that that it would be not too costly for compiler to implement, because the way the provenance mechanism is phrased somehow match the intuition that they have when they write alias analysis optimization. We don't have, however, I mean, if this is referring to the twin semantics, we don't have that requirement of having like double allocations, but we also don't do anything special for what happens when you run out of memory at the same time.
Okay, still have a little bit of time, so we can maybe go through a couple of more questions. So the next one is by Sagar Jha. How does Cerberus treat similarly unspecified portions of the standard, such as the behavior of padding bytes?
Padding bytes have the unspecified, so we have so unspecified values are also one of the aspects for which the C standard is not really clear. So we also have one proposal for clarifying them. And basically what we do is we lift every scalar type of C into morally an option type. And all the arithmetic operation over these types have a demonic behavior, which means that if, for example, you do a division and the second operand of the division is given the unspecified value, you would get the undefined behavior. And for padding bytes, like loading a padding byte is the unspecified value. So if you just do a copying of a struct, for example, that happens to have padding byte, you will successfully copy the struct. But if you try to do some arithmetic, you may get later on some undefined behavior just because it triggers a potential overflow in a sign plus, for example, or in a division.
All right, there was another question on arithmetic of obsess by Elliot Moss, but David Holland, I believe, answered that already afterwards. So maybe I go to the next one by Boris Jakubowski. What is the expected outcome of your discussions with the ISO-C committee? Refine the standard so that some currently used low-level idioms would be forbidden and some others would be unambiguously accepted?
So we would have a mechanism like the optimization that we observe right now would be explained, as in we would have phrasing that would explain how the C program can enter the then branch of the if then else I was showing you. Because right now this phrasing of the standard does not even allow you to make the conclusion that the program might go inside the branch while not producing the output that you would expect from the concrete semantics. So we would make more things well-defined, in particular manipulating bits of a pointer representation in the integer world as long as you reverse all your changes before casting it back. So we were both allowing more things, but also providing a foundation for justifying existing alias analysis-based optimization that we observe in Clang and GCC.
Right, thank you. I'm almost catching up with the questions as they are submitted. So next one is by Jian Kang. Would you please elaborate more on how to decide the right memory block for a past one pointer? I'm asking because it seems to be the most difficult problem we have to solve for pointer integer cast semantics.
Okay, so in our ideal model, we were just going to make it undefined behavior to avoid the problem, but that was not liked by the WG14 people. Instead, what we came up with is we have one more variant of provenance, which is so when we see that we're casting an integer value into a pointer where we may be one past a pointer or at the beginning of another pointer, we get a twin provenance. And the first use, which is going to, like the first time we use the pointer, because of the check of validity between the pointer and the integer value, there is going to be a collapse because we can't have both used to lead to a well-defined access. So the provenance will collapse to a provenance to one of the two objects. One of the nasty thing about that model is that now load morally becomes effectful on the go state. But this is the preferred semantics by the implementers we've been talking to and by WG14.
Right, maybe just to finish off one question that is a little bit more high level and too technical from Paolo Garuso. Can you simplify core by, say, partial evaluation to help programmers read the semantics of their C programs easily?
Yes, yes, we've done that. I haven't pushed it to the web interface. In fact, the current web interface is for a quite old version, but yes, we do have that, and it makes it far more readable, and I will make it accessible as soon as possible. And this is like the partial evaluation is done by, in fact, just using the operational semantics for core. So it's sort of like correct because it's using the semantics itself.
All right, thank you very much. And I see there's more discussion already on integer pointer conversion, and so there's more to be discussed on Slack.
I'll join that then. Thank you.
Thank you very much again, Karen. So our next speaker then, oh, we still have 3 minutes time, so let me stop this. All right, it's 10:02 on my watch. So our last speaker of today is Andrew Appel, who will talk about the verified software toolchain and convince you that this is a practical and powerful tool for proving functional correctness of C programs.
All right. Well, DeepSpec as an NSF-funded program was a 5-year program that is nearing the end of its 5-year period. So I thought I would talk about what's happened in the verified software toolchain, especially in the last 5 years. Prior to the beginning of DeepSpec in 2015, VST had been under development by several people who I've listed here on the slide. I worked on it initially with Sandrine Blazy as a kind of separation logic for C. Joey Dodds added a lot of proof automation. Aquinas Habor worked on concurrent separation logic, and Leonard Behringer did quite a few things. But in the last 5 years, I have this group of collaborators to thank, and we've made quite a lot of progress in the expansion of VST to be a really usable tool. So what is the verified software toolchain? At its core is a program logic for reasoning about functional correctness of C programs. The program logic is proved sound with a machine-checked proof in Coq with respect to the specification of CompCert's near front-end high-level intermediate language, C Lite. And then there's proof automation tools, a combination of lemmas and tactics that allow you to apply the program logic to your C program. Now, what are the challenges in building such a system? Well, the program logic might be too inexpressive to be able to do the reasoning you want to do about all the features of C or your C program, or it might be too inexpressive to reason about the mathematics of your application domain, which may be necessary for reasoning about the correctness of your program. C allows pointer data structures with complex patterns of sharing, as we've just heard in the previous talk. So the program logic has to be expressive enough to handle that. And C programs have higher order functions. That is, they pass function pointers in data structures that simulate closures or objects. And C programmers can program with patterns of data abstraction. The language itself imperfectly protects that data abstraction, but in reasoning about the programs, we would like to really reason abstractly. So what does a program logic look like for proving C programs correct? Well, since it's an imperative language, you might think we need a HOR logic or an abstract interpretation. So we choose HOR logic. And because we're proving things correct and not just safe, we want to embed this in a powerful enough logic to reason about correctness in whatever the application domain is of your program. So we choose to embed it in Coq, right? So that you can reason about your program's application domain no matter what it might be. C programs use pointer data structures, therefore our HOR logic should be separation logic. We want to prove modular C programs correct. So we need higher order logic, which is capable of sort of quantifying over abstract representation predicates and interfaces of modular programs. And since some C programs use object-oriented patterns, including such things as self-pointers, it really helps to have an impredicative higher order logic. So we get the impredicative higher order logic by using a step-indexed model. And then C programs have shared memory concurrency. So we need concurrent separation logic. So therefore, to prove correctness of concurrent modular object-oriented C programs that use pointers, we will use a higher order impredicative concurrent separation logic embedded in Coq. So that takes care of expressiveness, and much of this work had already been done by the beginning of DeepSpec, although not all of it. Now, if you prove a program correct with respect to the program logic, what does that really prove? And if you're not sure that your program logic really agrees with the compiler about the meaning, the semantics of C, then you have a problem. So that's why it really is important to prove the soundness of the program logic, the soundness of each inference rule of the program logic with respect to the semantics, and especially if you can do it with the semantics of that some compiler agrees to compile. And this means that if you prove a property of your program in verifiable C, and then you compile your program with CompCert, then you'll get a guarantee that the assembly language program respects the behavior you proved about the source program. And since CompCert's semantics is engineered to agree as much as possible with GCC and Clang and the ISO or C11 standard, especially when GCC and Clang don't happen to have bugs in compiling a particular program, then you even get meaningful, although not formal, guarantees about the behavior in GCC and Clang in the case where they don't happen to have a bug. So soundness was also mostly taken care of and proved before the beginning of DeepSpec, and you can read about it in this book. Well, the C language has many intricate corners, and therefore the proof rules for a C language program logic are intricate and non-trivial to apply to a program. And a higher order impredicative program logic sounds very intimidating. And in fact, users don't really have to learn about higher order impredicativity in the very, very, very common cases where they are not doing complicated object-oriented patterns using such things as self-parameters. So you can prove a lot of programs correct using the tool, thinking of it as a kind of first-order program logic. But you still need assistance in the form of tactical proof automation, applying a carefully crafted set of lemmas to help you apply the program logic to your program. So that's the VST Floyd interactive prover. And that's where a lot of the work has been done in the last 5 years, improving the verified software toolchain. But CompCert itself has evolved, and the CompCert C-Lite operational semantics has evolved. It's gotten more powerful and expressive, and occasionally a bug gets fixed in that semantics. So VST has also kept up with CompCert, and the current master branch is for the current release of CompCert 3.7. The next problem is this is all embedded in Coq, and so we need to make sure that it runs with reasonable performance. That is, proving runs with reasonable performance. We don't need to worry about the performance of the compiled code so much because CompCert C has respectable performance. And if you're desperate, you can always compile that same program with Clang or GCC. But how long does it take to run your proof scripts? And the good news is that although VST Floyd is not speedy, it is performant enough to be usable. It runs well in just a gigabyte to prove the correctness of reasonable sized function bodies. And because we support modular verification of modular programs, then you can run the verification of each module, or really even each function in each module separately as a different Coq process, and then link everything together. So let me give a little demonstration about what VST looks like to actually use. In Software Foundations Volume 5 Beta, we have the example of the verification of a hash table with external chaining. And the little hash function inside that program, as I show here, is very traditional. You could find it in a compiler textbook from 1986 if you looked. And so let's prove this program correct. It's a pretty simple program, but it does use arrays. And the first thing you notice is that it's not correct. It uses signed integer, it relies on signed integer overflow, which is ill-defined behavior in C. So let's write it correctly as a program on unsigned integers. And now this is correct, and we can prove it correct. So to prove a program correct, there must be a specification. And what we often do in verifying programs in VST is do a two-layer specification. We prove that the C program refines some functional model, And very often we write the functional model as actually a functional program in Coq, although that doesn't have to be written that way. And then separately, we reason about the properties of the functional model, which is possible to do in Coq then without reference to the original C program, just with respect to this functional program that Coq's logic is designed to be able to reason about. So here's our functional model. And you can see, if you can read functional programs in Coq, that it looks like it's doing something a lot like what the original C program is doing. And here we write an API spec. That is, the terms of discourse of the C program are sort of data structures using pointers and integers and arrays and so on, and they somehow represent the mathematical objects that the functional model in Coq is operating on. And this function spec in VST says that the function that's called hash in C has a precondition and a postcondition. And if the parameter value in the precondition is S, and in memory, the C string is a representation relation for C language strings null terminated. If S is an address representing the sequence of bytes that we call contents, then when in the postcondition, when you return, the return value will be an integer that's the 32-bit representation of hash fun applied to that sequence, where hash fun is the functional model that I showed you on the previous slide. And also that the string is still there in memory, unmodified. And because this is separation logic, we learn that more or less this function doesn't read from any other parts of memory besides this string, and it doesn't modify this string. All right, so the correctness theorem is called body hash here. It says that the F hash, that's the abstract syntax tree obtained by running CompSert's parser on the actual program. So F hash is the function body, satisfies the specification that we've just written down as hash spec. And we prove that by a kind of symbolic evaluation proof in Coq using the VST Floyd tactics. So let me talk more about representation relations. In the yellow box here, I've shown a representation of a C null terminated string as a sequence of bytes with a 0 termination. And we can write down C string just as a definition in Coq that's a representation relation between the value, contents, and its layout in C memory at address S. So in general, representation relations relate mathematical values, such as contents, to data structures, such as S. And EWS is a permission share that we use especially in our concurrent separation logic for saying whether you have read permission or write permission or whatever. Okay, so we can write down this definition C string as follows. It says none of the bytes in the sequence sigma, that should be a sigma there, not an S. Let me fix that. Maybe now is not the right time to fix that. None of the bytes in the sequence sigma are a 0. And in memory at address P, there is this sequence. It's sigma concatenated with a 0 byte. And this plus plus is just Coq's ordinary list concatenation. And then we inject that from list of bytes to list of C values. That's map V byte. And this data at is the separation logic maps to operator, but it needs to be parameterized by a C language type parameter. And the type parameter is array of signed character, so T array of TS char, whose length is the length of the sequence S plus 1. All right, so data at itself is the standard primitive representation relation for ordinary C language primitives. And from this, the user can construct slightly more abstract representation relations, such as C string, which is represents an array of non-zero bytes followed by a 0 byte. Okay, so before we prove correctness of this C function, let's prove a little lemma about the functional model. And the lemma I want to prove here is that if you cons something on to the end of a sequence, so that's called SNOC, which is cons backward, then you get a hash that's the hash fun of the original sequence times this prime number plus the byte that you consed. And so we can write that down as the lemma hash fun SNOC. And it has a proof in Coq that's not particularly difficult. Okay, so now here's what it looks like to verify a function body. Here I have the fun spec, the function spec that we wrote down for the hash function. And this body hash theorem says that the function body satisfies the function spec. And the proof goal in Coq is this semax body statement. So start function unfolds that proof goal to be a statement about a Hoare triple. And so here's the Hoare triple. Semax is our Hoare triple. Prop local sep is the precondition. Prop is the sort of pure propositional part of the Hoare triple. Local describes the contents of local variables right now, and sep describes the contents of memory, or of the separation logic portion of memory that this function observes. And then right here, starting with n gets 0, we have the actual function body, where the first line is displayed and more commands are sort of hidden in an abbreviation. And then we have the postcondition. Since we're going to do a forward separation logic proof, we will worry about the postcondition when we get there. And for now, we just abbreviate it. Okay, so if we unfold the definition of C string that I showed you the definition of earlier, we find that, well, the 0 byte is not in the sequence called contents, and there's a data at. There's actually an array of length of the contents plus 1 containing that contents concatenated with the 0 byte. And we're about to go forward through the assignment n gets 0. Now, before we do the assignment n gets 0, we have this precondition where the local C variable underscore s contains the Coq value s. And after we go through that statement, we have that as well. But we also have that n has the value 0. And now we've gone also forward through I gets 0. So we have that I has the value 0. Int.repr injects from the mathematical integers to the 32-bit integers. And vint injects from the 32-bit integers to sort of generic C values. Here's an array subscript. So we go forward through the array subscript. And this gives us a side condition to prove. So we have 2 subgoals now in the Coq proof. And we have to prove that the array subscript was in bounds enough for us to be able to reason about what we get. And this tactic for solving entailments, here's an entailment in separation logic. The entailer tactic assists with the proof of entailments. It can't always completely solve them, but in this case, it can completely solve that the index I is in bounds, or the index 0 is in bounds is really the point here. Okay, and now we've reached the while loop. And as you might expect, to proceed through the while loop, the user has to provide a loop invariant. So here's our loop invariant. It's written right here in the command forward while. And it says, that there exists an abstract mathematical integer I so that the C loop iteration variable I contains the representation of that I. And C and N and S have various values, and we still have access to this array in memory. There are 4 subgoals of a forward while. The first is to prove that the current assertion implies the loop invariant. That's just what you might expect in any kind of Hoare logic. And so that proof is written right here as exists 0 entailer. It's quite an easy proof. The second proof obligation is to prove that in each iteration of the loop test is safe to evaluate, that just the loop test itself of the while loop won't crash. And again, that's easily proved by the proof automation in this case, not necessarily in every case. Then we have to prove that the loop body preserves the invariant. And so you know, these 4 lines, forward through 2 commands of the loop body, make an auxiliary assertion about that will assist the array subscript in proving some things about the array subscript, forward through the array subscript, solve a subgoal by means of the entailer, solve another subgoal by the use of our theory solver for sequences with concatenation and subsequence. And now we've reached the end of the loop body, and it's time to show that our loop invariant is reestablished. Since a loop invariant is written with an existential, as is very typical for Hoare logic, we have to demonstrate a new value for the existential, and not surprisingly, it's going to be I plus 1. And that solves quite easily. But we still have a little bit of work to do, because in reestablishing the loop invariant, we're left with this subgoal, which says, well, we added another byte to the sequence. What happens to the hash function? And this is exactly where we can use our lemma about the mathematics of the application domain, our hash fun SNOC lemma, to solve this goal. So occasionally, in doing, you know, C refinement proofs, we need to reason in the mathematics of the application domain, and it's nice that we can do that modularly. All right, so, and again, here we've used a theory solver for the sequence, the theory of sequences and concatenation and subsequence. And then after the while loop is done, we have to prove the rest of the function body after the loop, which is fairly straightforward, and our proof is finished. Okay, so what have we been working on in the verified software toolchain the last few years? Many things. One group of improvements is in the expressiveness of the program logic. We now have an inductive Hoare logic, and I'll show you what that means. We have several new useful features for doing modular proofs of modular programs, including data abstraction, including the encapsulation of global variables, including sort of a clear abstract explanation of what it means to write separately compiled C functions that separately compiled .c compilation units that can call each other through linking. We've improved the program logic to better support various useful features of C, so that proving things about C programs with, you know, non-trivial control flow is much easier now. Support for things like strings, which are really just arrays, but where you reason about null termination. Floating point is now well supported, and we have support for sort of reasoning about C programs that might be in sort of 32-bit C instances or 64-bit. We've done several application case studies which teach us better separation logic reasoning techniques, such as, you know, how to use the magic wand to reason about partial data structures. In the program logic, we have good support for input-output and concurrent threads using ghost state. And when we reason about input-output, we have to reason about what that means to connect to an operating system, maybe even a formally verified operating system. We have several improvements in the proof automation. And in VST itself, as a software artifact, we have better process engineering. We have continuous integration and GitHub issue tracking, and coming very soon, there'll be graceful interaction with OPAM. Okay, so let me just talk about the inductive Hoare logic. Should a system like this have a deep embedded or shallow embedded Hoare logic? A deep embedded logic is a sort of a traditional logic. It has a certain set of syntactic operators that don't mean anything. It has a set of inductive proof rules, and then whatever you can prove with those proof rules is what you prove. And then you can try and reason about the consistency or the soundness of those proof rules. Shallow embedded logic has operators that are not just syntactic, they're semantically defined in terms of, for example, the operational semantics of the underlying programming language. And then the proof rules are derived as lemmas, and if you can prove each proof rule as a lemma, then you've proved the soundness. So which is better? And most program logics have been deep, but in our foundational proof carrying code project, 20 years ago. We used a shallow embedded type system, and that worked well for being able to prove the soundness of a non-trivial higher order impredicative type system. And so in the verified software toolchain, we have had a shallow embedded separation logic, and the iris system also has the similar kind of shallow embedded separation logic. And why shallow? Because it makes the soundness proof more elegant and extensible. And it also provides even some intuition about what the operators of your program logic really mean. Why not shallow? Well, here's an example. We cannot prove the equivalence of this reassociation of a C program because, in fact, it turns out the way that CompCert steps through these things, the command on the left takes a different number of steps than the command on the right. So they're not completely semantically equivalent. They should be in some sense, but that's not the compiler's fault. It's the fault of the shallow embedded program logic. So my student Qinsheng Cao a couple of years ago layered on top of VST's shallow embedded separation logic that's used to prove the soundness of VST, an inductive, deeply embedded separation logic, which is proved sound just by saying, well, each of these operators really corresponds to the same operator from the shallow logic. So we now have the user view that the user uses in VST Floyd is a deeply embedded separation logic. Most of the time, the user can't tell the difference, but there are some additional rules that are made affordable to the user. And here's an example. We can invert rules such as the sequencing rule. From P, C1, C2, R, we know in an inductive Hoare logic that there must exist an intermediate assertion Q so that the triples P, C1, Q and Q, C2, R are provable. And that's useful enough for reassociating sequences, but in the control flow rules, it's even more useful. We get a lot better reasoning about control flow by having the ability to invert rules. So there's a question in the questions thread. It seems like in the hash fun example, the instantiations of the existential quantifiers could be easily inferred via unification. Does VST support this, e.g. by instantiating an existential quantifier with an evar? And the answer is yes, especially since about a year ago by the work of my student Jinshi Wang, who has put a kind of e-exists into the VST Floyd system and demonstrated that it works pretty well. Okay, so I talked about C strings in the program logic and about Jinshi's theory solver for sequences and other VST Floyd proof automation demonstrated in the hash example. Let me talk briefly about floating point. Here's a little floating point program written by Freek Wiedik. It's Newton's method computed, its square root, floating point square root computed by sort of a naive application of Newton's method. But Newton's method is pretty good, so even a naive application of Newton's method is quite efficient. And here's a functional model for that C code. It's just essentially a similar program rewritten in pure Coq, but relying on this float32 library that's really the sort of flock formalization in Coq of IEEE standard floating point. And we can prove quite easily that the C program correctly refines that functional model. The specification is fairly straightforward to write down. The proof is fairly straightforward to do. And this proof is fairly straightforward to do without knowing anything about Newton's method or floating point or even square root. But what you also want to know is that f square root function, the functional model, correctly implements floating point square root. So here's a theorem proved this spring by Yves Berthaud that this is correct with down to 5 times the least significant bit precision of single precision floating point. Single precision has 2 to the 23, or has 23 mantissa bits. So 5 over 2 to the 23 is 5 times the least significant bit. Eve believes that he can probably prove something stronger about this, that it's even more accurate than 5 times the least significant bit, and he can improve the range of preconditions for which it's this accurate, but this is the proof we have so far. And what we prove here essentially is that that this is correct with respect to floating to real number square root as axiomized in the theory of the reals in Coq, and that float to real sort of commutes with floating point square root and square root to that level of accuracy. So we want to compose these two functions, and for this we can use a new feature of VST designed and implemented by Leonard Beringer, which is fun spec subsumption. We can prove this stronger specification for Newton's method square root, that if your argument is in a certain range, then your result is this accurate with respect to actual real square root. And we can do this without redoing the refinement proof. We can just compose these two theorems together quite simply. And in just a few lines of Coq, we get this stronger specification. Okay, so let me turn to the questions. Can I clarify the inequivalence of these C1, C2 quantity semicolon C3 or C1 semicolon quantity C2, C3? If the Hoare logic asserts P eventually gets to Q, then it shouldn't matter if they take a different number of steps. But in fact, in a step indexed program logic, which we have in order to support these higher order impredicative programming patterns, then it turns out very annoyingly that it does matter if they take a different number of steps. And that's why it's sort of useful to layer the deeply embedded logic on top. And Peter Sewell asks, what range of specification styles have worked? For some examples, there's a very natural functional model like the square root Newton and so on, but for many chunks of C, that's presumably not the case. Indeed, the functional model does not have to be a functional program. And for non-deterministic C programs, for C programs with some amount of reasonable and permitted randomness or non-determinism, then there is no single deterministic function that's going to work. So sometimes the appropriate functional model is some representation of graphs and relations on graphs. You can use a relation in Coq instead of a function just fine as a functional model, and without particularly more difficulty, prove the refinement of the C program to the relation. When we can use a function, we do, not because it makes the refinement proof easier, but because it makes it often easier to reason about the mathematical properties of the functional model. Okay, so we have these layered proofs where, as I've shown, at the bottom layer, we have the C program. At the middle layer, we have a functional model. And at the high layer, at the highest level, we have the mathematical property that the user really wanted from the program. And then we can compose two separate lemmas. And so we'll call these the high-level spec, the functional model. Some people call that the low-level spec, and the C program. And indeed, I showed you the same kind of thing for the hash function with its functional model as a functional program in Coq, about which you could reason about what kind of collisions you're likely to get on various short strings. And if we think about these three levels and the two proofs in between them, there is a good modularity of expertise in who does the work. Some software engineer writes the C program, and some requirements engineer writes the high-level spec. And in the case of crypto, for example, some standards engineer at NIST will write the functional model. That's what NIST, the sort of standard specifications of cryptographic functions look like, is some mixture of LaTeX and English and math that describe an algorithm. And from that, you can go up and prove the properties of that algorithm in the computational monad of probability spaces. And going down, you can do the refinement proof. These two proofs can be done by quite different people. And what we found in practice is that the application domain logician who does that high-level proof doesn't ever need to look at the C program and doesn't need to know anything about the use of VST as a program logic for C. And the separation logic specialist who does the refinement proof doesn't actually need to know much of the mathematics of the application domain. So you can build teams in this way. There's a question about what about failure handling in C code? And I'm not sure what the question means. To the extent that the C program has undefined behavior, then the program logic won't be able to prove anything about that part of the C code. Or if the C code calls the Linux or POSIX exit function to abort, we can write a post condition for the exit function, which is to say false, and that's easily accommodated in the program logic. Okay, so I have a couple of minutes left. I'll talk about 32-bit or 64-bit C. C programs can be implementation dependent because the size of pointers can be made to show up in the semantics of C programs just by doing size of. And therefore, we can write a post condition for this function, and this function will be provably correct with respect to this post condition on a 32-bit machine, but not correct on a 64-bit machine. So you can prove this correct in VST for a 32-bit machine, but you can't for a 64-bit machine. The program logic itself is parameterized by what kind of C installation you're proving with respect to. And therefore, the proof objects that are produced by QED and Coq cannot be size portable. But you can, with some care, make the proof scripts size portable so that the same program, which you think is portable, when compiled for a 32-bit machine or a 64-bit machine, the same proof script can be rerun once for 32-bit mode and once for 64-bit mode and prove it correct. All right, so I think I will skip over this example. Here's a little example about insertion in a binary search tree using a clever arrangement of pointers. And when you're halfway down the tree, you've got the part of the tree above you and the part of the tree below you. And these have to star in the separation logic sense. And as we have become better users of separation logic to prove things about C programs, we learn better how to sort of use the magic wand as a kind of framing technique for the data structure that you have walked through. Okay, and I won't talk in any detail about the recent work in modular verification of modular programs, which is now well supported in VST, nor about the work in sort of Iris-style reasoning using ghost state about input-output, about concurrent threads, and our very and our own foundational connection to the operating system. We had a paper last year showing that you can write a client program for the Certicos verified hypervisor kernel, where the client program is proved correct in VST, and the implementation of the system calls that it makes are proved correct in the Certicos proof using concurrent abstraction layers, certified abstraction layers. And we can get a foundational proof that crosses the boundary there in Coq. Okay, so last year, Fred Wiedik put out this benchmark suite for C program verification with 25 programs that exercised as many corners of C as he could, and he challenged makers of C program verification tools to prove them functionally correct in the tool. And the current score, as far as I know, is that out of a possible 100 points, Verifast has 4 points, and the verified software toolchain has 47 points. And of course, in each case, it would be possible to get more points, but not all the points, by doing more work applying the tool to the examples. And with that, I will conclude. So now let me take care of the next few questions. What kind of reasoning and soundness theorem does VST have for concurrency? So this was the work of several people in the VST project, but principally the PhD thesis of Santiago Cuellar. And we have a tech report from the spring of this year showing exactly which extension to CompCert will support correct compilation of concurrent programs. That's a slight extension to CompCert's operational semantics, and then we can prove the correctness of a higher order concurrent separation logic in VST with respect to that semantics. And there are sort of ghost state reasoning tools and proof automation tools built by William Mansky that allow you to use that kind of system. Proofs cannot be size portable is a strong statement. Why not model the bit width as another piece of state that can be mentioned in the preconditions? Well, what I meant is proofs in VST can't really be size portable. One could, in fact, imagine designing a different program logic that supports a little bit more abstraction in that sense. Another question is, sometimes a program written slightly differently is much easier to prove. Are there programs particularly well or badly amenable to VST? Indeed, that's true. And sometimes we find it's convenient to tweak a program or throw it out and completely rewrite it. But one of the goals of this project was to be able to verify so-called dusty deck programs, especially in the case where they're actually correct. And so, you know, we would like to at least have the capability to verify programs as they were originally written. And I'll ask, are there more questions? What are some of the complexities in the programs in the verification benchmark suite that couldn't be handled by current VST? That's a good one. I'm trying to remember. In some cases, the benchmark programs are just quite large, like the entire glibc malloc-free system that in principle could mostly be verified, but we just haven't done yet. We do have a paper that's going to be presented tomorrow in the Memory Management Symposium about a verification of a simple but efficient malloc-free system. There are some very clever floating point examples that pun on the representation of integers and floating point that can in principle be handled by current VST, but only by an expert in proving things in Coq about floating point representations, which we are not. And until recently, we didn't really have a way to handle printf. And now we have a way to handle printf that's not really foundational, but is usable. So those are some of the complexities. And since I see no more questions, perhaps I should wrap up.
Right, thank you very much. Since Andrew already answered all the questions there are, there's not very much for me to do. So I think we'll just wrap up for the day here and thank all our speakers again. And we'll meet again tomorrow at the same time as today. So thank you very much.
Thanks, everybody.
is the root of all evil. I don't believe in step indexing. No, that's wrong.
Hello, Leonard.
Hello. Yeah, I haven't officially ended the meeting yet. I guess the recording on YouTube by now should at least stop.